Welcome to Programming Robotic Systems with Visual Studio. My name is Chris Howd. I'm here with Paul Party. Yep. And let me just tell you a little bit about myself to get us started. Been with Microsoft now for about 12 years, but I started out as a mechanical engineer working for the Department of Defense. While I was there, I was really involved in a lot of systems programming projects where we would automate measurement systems and control simulators. So that's how I got into robotics and into programming. After working for the Department of Defense for about 10 years or so, I went on to have my own company for a while, and then I joined Microsoft about 12 or 13 years ago, and I've been working to support the developer audience since then.
Cool. My name is Paul Party. I've been at Microsoft for about 20 years. I worked in a variety of roles, but mainly roles that focus on software development and content. So I've been with this training org for about a year now, and I've also done a lot of software development for the company and personally. So I have a Windows 8 app in the App Store and a Windows Phone app in the App Store. I've also worked on technical content, technical training. I have a book that I wrote back in the 90s, co-authored on Microsoft Access, if you can believe that. It's been a while, but I had a lot of fun doing that. So I've been involved in software and with Microsoft for quite a while. Been in the industry for over 20 years. So I'm really looking forward to this session where we're going to talk about robotics and embedded systems. So let me spend a little bit of time walking you through what we're going to be doing today. We've got a lot of really great stuff. We're going to talk about the target audience in just a moment, but this course is really aimed at getting you introduced to robotic systems and what robotics is all about. So let me just talk you through a few of the modules that we're going to cover today. So in Module 1, we're going to introduce robotic systems and embedded systems. We really want you to think of this course beyond just robotics. Robotics is kind of the hobbyist arm of what we're going to be talking about. Really, this is about embedded systems. We're going to use the term Internet of Things. That's kind of the popular term these days to talk about these kinds of things. We're going to talk about that a little bit later, but it really is broader than just robotics. This is to get you introduced into that whole topic. So we'll do that in Module 1. In Module 2, we're going to talk about a technology called Arduino. Arduino is essentially a board, a hardware technology. Chris will walk you through what an Arduino board is. But Arduino is a really great system to get started with. It's accessible financially. They're cheap boards. Inexpensive, I should say. They're not really cheap. Inexpensive boards, but they're easy to program. So really great technology to kind of get you going in this space. And we'll talk a little bit about those. And then in Module 3, we're actually going to walk you through creating a robot. So we'll talk about how we did it, how we put it together, and we're going to use Arduino as the basis for those robots. We have a really cool robotic arm. You'll see it when you see the wide shot over by Chris. Chris put this robotic arm together. There's a lot that goes into making that robotic arm work, so we're going to talk about how we put that together and how you control a robotic arm like that. We'll spend that time in Module 4 walking through that. And then in Modules 5 and 6, we're going to talk about sensors. So a really cool thing that you can do with robots, obviously, is make them autonomous, where they can navigate a space, where they can move around within a confined space, or even roam hallways or whatever. And the way that you can create autonomous robots is by giving them the ability to detect what's around them. So what we're going to do in 5 and 6 is talk about what those sensors are, talk about the various sensors that you can use, and then in 6 we're going to talk about how you map the space, how the robot will map the space that they're in and detect the area so that they can navigate that space and detect other objects as well. So that's what we'll do in 5 and 6. And then 7, we'll kind of close out the day by looking at wireless controllers and how you use wireless to actually control a robot rather than having the robot be autonomous. So that's where you can get into a lot of fun. You put a little wireless controller on the robot, and then you either use your computer, your cell phone, whatever, to make the robot do what you want it to do. So we'll kind of close out the day with that. You'll see a spider here on the desk later on when you see a wide shot, and that spider is going to be controlled remotely. And then finally, we're just going to look ahead to see what we want to do next in this series, and we certainly want some feedback from you and to hear from you on what you like to see. Okay, so that's kind of what the series is going to be about. Chris, did you have anything to add on that?
No, I think you covered it, Paul. That's good.
Great. So let's talk a little bit about the target audience. So is this for you? we really want to focus this course on developers and hobbyists. So if you're a software developer, this is really geared towards you. We're going to look at a lot of code. We're going to show you how you program these Arduino boards. We're going to talk a little bit about the .NET framework and some other technologies that you can use. So we really want developers to understand how robots can work for them. And as we think about the Internet of Things, as we think about wearables, as we think about home automation, developers are going to be a critical part of that revolution. So this is a really emerging field that we think is super exciting. Microsoft's going all in on this space, and we think that developers can really benefit from this technology. So we're gonna talk to you developers today and hobbyists so that you can learn how to do this type of work. And then in terms of prerequisites, what do you need to know? Well, some basic programming skills are going to be important. So we're going to show you how to program these robots using the code that the robots can understand. But if you know basic programming, you can pick up on this stuff very easily. They're standard routines. We're not going to show you anything that's super complicated. But it would help to have some experience with programming in general. If you don't have that basic programming, you might want to check out some of our other MBA series. We have some C# fundamentals, some courses in C# fundamentals, programming in C# and our JavaScript courses. All would be good to check out before you watch this series. But again, if you just have basic programming skills, even web programming, you'll do fine and you'll be able to navigate through the course. So that's kind of the frame. That's how we're going to frame the work today. And we think you'll have a great time. This is just a super fun space, and we think you'll have a great time doing it. Very quickly, I just want to point out that this is a part of the Microsoft Virtual Academy series. This is free training. We've got over 2 million registered users. Really exciting space, and we encourage you to check out the rest of the series, the Microsoft Virtual Academy courses, and encourage you to visit that often. We're always putting new stuff up almost every day.
Yeah, absolutely.
All right, I think we're ready to get into the fun stuff. So let's start with Module 1, Embedded Systems, Robotics, and how we're going to talk about that through this MBA training series. So very quickly, let me talk about the module, what we're going to do here. We're going to spend a little bit of time talking about what embedded programming is and use robotics as the introduction to that. You see that acronym IoT, Internet of Things. We're going to spend some time talking a little bit about what we see as the Internet of Things and how that relates to the work that we're going to do here today. We'll show you some microcontrollers and some hardware. A lot of fun things we brought in, some toys that we can show you. We're going to give you some examples of some microcontroller boards. We're going to use very specific ones in the robots we've created, but there's lots of others that you can use, and we'll show you some examples of those. You also have options when it comes to software. We're going to do a lot of our programming in Visual Studio, but there are other compilers that you can use to communicate with the robots. Visual Studio, obviously, we think is the best one. It's fast. It works extremely well with the system that we chose, but we'll show you some software options. We'll walk you through some code samples. Of course, we want developers to get a running start with this series, so we'll give you some code samples to use. We'll post those code samples later, obviously, to Microsoft Virtual Academy. And then we'll introduce you to the robots. We'll talk about the robots we've used, and then we'll show you how they work. And throughout the day, we're going to be doing a lot of demos. We're going to be showing you the robots constantly. We have a little pen set up in the next room, the next studio, and we'll be kind of going back and forth. So we got a lot of fun stuff for you today. All right, I'm going to turn it over to Chris now. He's going to talk a little bit about this whole space and Microsoft's history with this space.
All right, very good. Thank you, Paul. As you said, Microsoft has a big role in embedded systems, very important to us. When we think of embedded, a lot of times we think .NET Micro Framework, which is our typical, it's our version of .NET that we use for programming embedded systems. But there's a lot more, right? We have this course. We focus on robotics. It's going to help you with other embedded cases, right? Whether it's Internet of Things or even if you're programming hardware with a tablet or a PC, right? So, will we get onto more robotics in this series? We hope so, right? I mean, that's going to kind of be up to the audience, right? You tell us you want more on robotics. We're definitely going to do it. That's our thing. Now I'm going to talk a little bit about microcontrollers and other hardware, right? So if you're building a robot, you have to have a microcontroller, right? There's a lot to choose from. How do you make these choices, right? Think about the processing power that you need, right? Think about the other sensors that you're going to be interfacing with. Those are the two big things, and there's cost, right? So, but if you need to buy this stuff, it is everywhere on the internet, just everywhere. I would say search for robotic systems or search for robotics hobby, maybe even better. You'll find a lot of hits. Getting started, a couple of different ways to do it, Paul, right? You can either get a kit, a lot of really great kits out there, or you can just dig in with a system like the Arduino systems, and they're really simple to program. We're going to be showing that in just a minute. First, this next slide, we're looking at, these are some examples of some of the boards. Paul, you and I have some boards here with us as well. Let's see if we can get, maybe switch over to one of these other cameras. On the screen right now, you see an Arduino Uno in the upper left, followed by an Arduino Mini, an Intel Galileo, might have heard about those. And then in the middle, it is an Arduino LilyPad. On the bottom left, this is kind of a cool one, right? This is a .NET Gadgeteering standard board. So that means you're plugging in modules to this. You don't have to solder wires together and do stuff like that. It's plug and play. Well, it's not plug and play. It's you plug and then you play.
It's a lot easier to play with, yeah.
Next to that is a NetDuino Go. And on the far right bottom is a NetDuino Plus 2.
Now, Chris, how do you navigate this? Like, how do you know which one to start with? How would you pick one?
There's a lot of support for the Arduinos. That's a nice place to start.
Yep.
If you're afraid to solder, maybe something else. But either one of those is good. I would say, stick with the Arduino. This is what we're going to show you, right? Yeah. We're going to show you the Arduinos. We had a reason for that. It's a big industry standard. There's a lot of support out there. It's pretty simple to program your robots with this thing. That's what we picked it. I'd say go there. Get a kit if you want. Kits are great, right? So, let's just keep this moving. Should we show some of these that we have here, Paul?
I think we should. Let's just hold up some.
So,
of them. Go ahead.
Yeah. Okay. So I have a couple of Arduino clones, actually. So a clone is just, it's a person's representation. I'm holding this up here. Here you can see this thing. Looks just like the Arduino Uno that you saw, and it's just manufactured by another company. It's a nice little board. Here's another one. This is a little bit bigger. Also an Arduino clone. Get a shot on that. And you can see these have little headers here on them, where you can plug pins in, and then the processor board, and a connection for your PC and power. Paul, I don't know if you want to try and show any of these?
A couple here. So I've got the Arduino Plus. I don't know if the camera's going to be able to get in here. There we go. The thing to notice about these, and this has kind of shocked me when I was first getting into this, is just look at the size relative to my hand. They're pretty small boards, and you can do a ton of work with these little boards, and I think that's kind of exciting. So when you think about embedded and you think about Internet of Things, the boards aren't that big. They're really thin. You can stick them just about anywhere, and of course, the boards are going to just keep getting smaller and smaller. So you can do a ton of work with. And
the great thing about the NetDuinos, right, is it runs the .NET microframework.
That's right.
Which is very cool.
Do all your programming
if you're familiar with Visual Studio and programming in .NET, it's just an extension.
That's right. And I just got one other I want to show here. Maybe if we can zoom in on this camera here. So this is this kind of looks spidery looking thing. Maybe you want to talk about this a little bit, Chris? What do you got going on?
Sure, right. That is the NetDuino Go, right? We talked about .NET Gadgeteering. NetDuino Go, another version of that, right? And it's a kind of, you plug in the little modules. Let's see, we have some
that kind of turns.
Yeah,
right?
Yeah. We have potentiometer, some buttons, some little audio buzzer maybe, and then the thing at the top that you're holding on. The bottom. So down at the bottom, that is a shield that is pin compatible with the Arduino system. So you can actually use shields, which we will be talking about pretty soon, Paul. You can use your shields from your Arduinos with the NetDuino Go.
Which is really cool.
So it's pretty cool. So
you can extend the power of these boards by using these shields. We'll talk about that later.
Yeah, and that's a beautiful thing.
That is.
All right. So then software options, right? Okay. Hey, it's going to be dependent on what your board is, right? If you're programming, if you have an Arduino board, then your programming options are, compatible with the Arduino system, which is like a C++ type of language. But if you got a different board, then you're going to be programming a different language, right? So if your robot is using a PC or a tablet, then you're going to be programming your options are wide open, right? Your architecture, it's going to be similar to any program that you're writing. You want it nice and modular. You want to control your different systems. You want to keep it responsive, right, in the same way that your program would be responsive. It's just you're not responsive in the UI. You're responsive in the hardware. So it's a little bit different. Taking your first steps, right, keep it simple. We're going to be showing you the Arduino boards. It's a nice, simple system. We'll start out easy. But
we do have a code sample here, right? We want to throw up?
Yes. Yeah, so this code sample, like you say, all right, yeah, this is great, right, Paul? This is great. So what we have here, this is very typical, and we'll be talking about it in just a little while, but this program loop, the void loop, is your main loop for your robot with an Arduino system. And you can see the code looks very similar, right, to what you're familiar with. You want to check and see if your robot is initialized. Maybe that's a good first thing. It's up to you guys, right? You're going to be writing these codes, developing these systems, but it's nice to make sure you're initialized first. Then you're going to do some checks. You're going to do this and that, and you're going to get onto your live robot thing, right? But the important thing is it looks familiar. It's doing a little bit different stuff, but it's familiar code.
That's right. And when you were walking me through this, the thing that also again was surprising is that it is fairly simple to get going. It's not like you have to write hundreds of lines of code to get a robot to do something really cool. And you'll see this as we get into the actual code that we're going to use to program the robots that we have here. But it's not a lot of programming, and as you mentioned earlier, Chris, it's simple. Like you can get into it, and these are things that you've done before if you're a developer. So really cool way to get started very quickly.
All right, Paul. I think now we're just going to talk about the robots. We have 3 robots,
correct, that
we're going to be using. The first one, Paul, is over next to you. That's just this simple autonomous robot that's going to move around. It's going to bump into stuff. When it bumps into something, it's going to change direction.
Sure.
Go forward, back, turn, do whatever. So that's a pretty simple one. The second robot is over near me, Paul. It is this one that you mentioned has an arm on it, but it's a little bit bigger, and it's got the arm. It's got more powerful wheels. It's got DC gear motor wheels, and then it has these sensors on it, so it can look around. So I would say that the MS Bugbot, we're calling it MS Bugbot, right? That one is just purely kind of a dumb little thing that wanders around, right? This one's kind of more semi-aware, right? Because it can sense its environment. It doesn't have to run into something to know what's going on. So it's a little bit more aware, and this one's going to actually map out the area and detect another object that enters its area.
It's very cool to watch.
So it's kind of cool. And then the final one, so these first 2 were autonomous. The third one is this MS Spiderbot. And that one we have set up with a wireless RF system, so we can actually control this one from a PC or another device, right? So those are the 3. The other big difference with the MS Spiderbot, right? It's not wheels; it's using legs. A little bit more complicated. Not your place to start.
That's right.
Right? Not the place to start.
You're moving 8 legs instead of.
So, Paul, the next thing we're going to do is we're going to have a little demo.
Let's do it.
Of these bots. So
awesome. All right. So we're going to now show you these robots. We're going to show you a little bit what they can do. We're going to move to another studio, and we're going to show you the robots in a little pen that we've built, and we're going to show them moving around. So
right. This is going to be fun.
Yep.
All right. Welcome to Studio B. I am here to show these robots. We got the MS Bugbot, we got the MS Guardbot, and we have the MS Spiderbot. I'm going to give you a quick demo of each one of these, maybe talk a little bit about them as they're moving around. I'm going to do them one at a time. I'm going to take these guys out, put them over here, and here is our MS Bugbot. This guy is just going to wander around. He's going to bump into a couple of walls, and he's going to change direction. That's all there is to it. So it gives it a little bit of time. He's initializing. He's going to start up. Here he goes. All right. Which wall will he pick? And he bumps in. Okay, he's going to watch the sensors, and he's going to have a little failure. Let's try that again. All right, he's going to try it again. He's a slow learner. All right, he's warming up. He's initializing. Here he goes. The problem is the wall here, the plexiglass, has a little bit of give to it, and he bumped off of the wall before he was ready. All right, now he's going to move back off. He's going to pick a new direction. He's going to go off. I think you get the idea. That's what he's going to do. He's going to hit another wall. We'll let him hit it, see if he makes his right decision here. Okay, looks like he's going to go good. He's going to move off, and there he goes. All right, you get the idea. Come over here. Come here, you little guy. You rotten little... All right. That's pretty boring, really. But now, we have this guy. This one we said is semi-aware, right? That's what we said. So what he's going to do, he's going to initialize as well. Now he's looking around his area. He's got these ultrasonic sensors. He says, oh, hey, here's a wall over here. I think I need to align to that wall, because what he wants to do is map his area. Right? So now he takes his readings with his sensors, and he's saying, hey, one's bigger than the other, so I'm going to spin a little bit until both are reading about the same thing. Then he's going to start moving towards the center of the area, and then he's going to read his coordinates. All right? Now he's moving out towards the center. He's going to take a little bit of time to get there. And a little bit more. Okay, now he's going to try and rotate 90 degrees. Oh, nope. Now he's going to keep moving. All right, he's looking around. He says, oh, all right, here I go. All right, a little too far. Now I got to move back. All right. I think you get the idea. He's going to move out to the center. Then what he's going to do is he's going to start looking around. We can let him get to that point. It'll just take a little bit longer. He's going to align to the other wall. Remember, he's mapping his area, right? So he's going to align to this wall now. He's going to say, okay, I'm there. Now I'm going to move into the middle. Now I'm going to start scanning the area and seeing if something new comes in. And maybe I'll be dangerous. I'll stick my hand in there and see if he goes nuts on me. What he really will do is he will deactivate. We're going to add a little extra to the MS bug button. He will go and deactivate him. So he's getting close to the middle. All right, now he's scanning the area. Now he knows where the walls are because he read where the walls were. Now he knows, so he's saying if something new comes in that's not within the range of the walls, then it's something different, and I need to go and I need to deactivate it because I'm the MS guard bot, right? So I'll just put my hand in here, let it get through this cycle. It's going to see my hand, and it's going to say, hey, wait a minute, I think. All right, we'll get that squared away. Oh, there he goes. All right, he saw me. He's going to come over and he's going to say, you're naughty. I'm going to get you. All right, that's what he does. All right, and the last robot is the spider, MS Spider Bot. It's a little bit different, right? We talked about this guy. He is remotely controlled, so I'm going to send him some messages from over here. Just power him on. All right, he's going to initialize. He's ready to go. All right, I'm going to send him a command to move forward, which I don't know which is forward for this guy. He's going to move towards me. All right, fine. Now I'm going to move him backwards. All right, he's moving backwards. Let's spin. And you kind of get the idea, right? I'm over here on my PC. I'm sending this little commands with a little radio frequency commander and router pair. We're going to talk about those coming up. But that's what we got. They'll do a few more tricks for us when we get to them. All right, so those are our 3 robots that we're going to show you how to program these things. We're going to show you how to work with the sensors. We're going to show you how to work with the different motors that they're using. And that is it for the demo. We're going to wrap up Module 1 now. We'll see you back here. Well, actually, we'll see you back in the other studio for Module 2.
Hi, and welcome back to Programming Robotic Systems with Visual Studio. I'm Paul Party, and I'm here with Chris Howd. And we've been working on building these robots and showing you a little bit of what robotic systems are about and actually how to program them. If you missed the last module, you'll definitely want to go back and check it out. We introduced our 3 robots. We showed you kind of what they can do. And now what we're going to do is walk you through how these robots were built, how they were constructed. Chris built all of these robots from scratch. He essentially cut the plexiglass, he bought the boards, put the wires in the boards, constructed the system so that everything works together. So everything that you see was essentially built from scratch. There's no pre-assembled parts. So
We're not suggesting you do that.
right, but it is an option. So you can kind of see how we did it from starting with nothing and then building a robot from these parts. Okay, so let me walk you through very quickly what we're going to do in this module. So first of all, we want to introduce what Arduino is to you. So we're going to talk about the boards themselves. If you don't want to if you don't want to actually buy an Arduino board, you can actually buy a clone. So we're going to talk a little bit about what clones are. And then there's these things called shields, and shields allow you to extend the power of the board itself. So if you want to do other things, and Chris will talk a little bit about what those other things might be, you might want to buy a shield so that you can extend what the board itself can do. Then we'll get to the software. This is the part that I think all you developers will be very interested in. We'll talk a little bit about how the software works. The reference libraries, we'll show you those a little bit so you can get a feel for them. And then we'll show you how you can integrate the Arduino system with Visual Studio, so you can actually program the Arduino boards right from Visual Studio, which is fantastic. You get all the power of Visual Studio, but you can program your robot using that. And then we'll walk you through a quick demo. In Arduino, the programs are called sketches. So we're gonna walk you through a small sketch, and you can see how these programs are constructed. So with that, I'm going to turn it over to Chris, and Chris is going to start to walk us through this Arduino system.
All right, okay, here we go. What's our slide, Paul? What are we talking about here? Arduino boards? What is Arduino? Hey, all right, very good. Arduino, so it's an open source standard, right? Hardware and software. If you want to get the schematic for the boards, you get that schematic, print out your own thing, do your whole thing, you make all from scratch.
Yep.
Open standard, right? So it's kind of different from open source software, a little bit different, but it's the same idea, right? So then the programming language is very easy, right? It's C, C#, C++, any of those languages, JavaScript, Java, those things, easy. All right, programmable via USB, right? USB board, right? Very easy to connect. Then it's affordable. Affordable, popular, big open source standard. Lots of people using Arduino. Good community. Lots of people help you out if you get stuck. So that's nice. What else about Arduino?
So actually, I have a question. So those little boards that we showed earlier, I have one here in my hand. What does a board like this run? Like either a clone or
Very good. Cost. Okay. So the Arduino started around $25 or so for like an Uno, and it goes up to maybe $70. So they're pretty cheap, right? I mean, pretty affordable, as you mentioned earlier. So cost is pretty reasonable, and it's extensible through the shields, as you said. I think we're going to talk about that a little bit, but we're talking about the Arduino products right now. So I have the website open. If we just switch over to my monitor, we'll look at some of these things here. So you can see there's quite a few to choose from. And this is showing us both the boards and the shields, and you can get a kit. It's nice. There's lots of other kits that you can get as well. We're using the Arduino Uno, and we're using one down here a little bit further. It's I don't see it actually, but it's 2560. There it is down there. You got these lily pads. You got all kinds of stuff, right? The ones that are different, let's see, like this Explora, there's a few different things that are set up that aren't pin compatible. They're set up for something different. We also have the Mini and Micro. Those also go for like breadboarding. And we have the Yun here, which has Ethernet ports for connecting up to your network. All right, so that's the basic thing.
This can look a little overwhelming when you come to a site like this. What we're going to show you later, as we get into how we built the robots, is how you make a decision. Which board should you buy? Yeah. Which shield should you buy? So we're going to give you some guidance on how you navigate this wide variety of options and pick one that's right for you.
Right. Very good. Let's switch back to the slide deck here. Okay, so we've talked about boards. There's clones available, so you can get clones. Paul, you were asking about price. You can get some clones that are even cheaper. You can get clones maybe even down to $15. So look around for those if you want. And then we have shields and accessories. Okay, Paul, you mentioned that you use shields to extend the capability, so that's correct. So you have some basic functionality on the board. By being able to provide boards with basic functionality, they keep the cost down, but they're extensible through the shields. So these shields add onto the top. We looked briefly at one of these boards, and you could see the little headers, they're called, with pin slots in them. So you add these shields on. You can get shields that do motor control. We'll be using those. You can get shields for communication, for networking, for audio, for video, for anything. It's huge, huge market. Then back to the slide deck again. Help me remember what we're talking about. Okay, well, let's go on to software maybe.
Let's get into it.
All right. All right. If we look back on my machine again, we go to the Arduino home. I'm getting there, I think.
Yeah, we're going to quickly look at the language reference so you can kind of get a sense of what things look like.
But for installing, there's a download site here. So you're going to go right there. You can install for Windows. I believe it's buffering a little bit.
That's
here.
right.
In any case, so there's installation for Windows. There's also installation for some of the other popular operating systems for PCs. So it's pretty good in terms of installation. Just click on it. And that will load up your programming environment, your integrated development environment like Visual Studio has, only not quite the same way. So here's the Windows installer. It also supports Windows 8.1. You see the little note here. Okay, so let's say we've installed the software, which you and I have, right? Mm-hmm. And it's just on our PCs. And then you want to know a little bit about the language, I think you were saying, Paul. So we look over here. There's a reference still on the Arduino website. We see that they provide the language reference. Now this is going to look surprisingly familiar, Paul. All right, fine, you have some structures, you got setup and loop. These are the two main always present programming loops. In setup, you do your setup, you configure your variables, you configure your hardware. In loop, that's the main program loop. You loop through that, it loops. You want to keep that looping quickly, right, so that it's responsive. But that's where you put in your calls to your other functions and you do your main programming. The control structures, if, else, for, switch, all these things, those are very familiar. The other syntax is also familiar if you've done any C, C# programming, JavaScript. All that looks pretty similar to what you've seen before. Same thing with the data types and constants. That's all pretty familiar stuff. There's maybe some terms in there a little bit different, but the concepts are all the same. We get over to functions. Now this is going to start looking different, right? Because a lot of these functions are referring to hardware. Pin mode, I mean, what is that, right? Digital write, digital read. Well, I kind of get the idea, I mean, I understand digital. It's kind of like binary, right? It's either high or low. Then analog, okay. Voltage, right? Analog voltage. Then you get this pulse width modulation, PWM. That's one of the things we'll be doing. We're going to use that to control our servo motors. We're going to skip past this. It says it's for a board that we're not using. Some advanced I/O, tone, no tone. I'm thinking that's some sound, right? Some time functions. I mean, we get those, and then some math functions. That makes sense. Random numbers, okay. Nothing crazy there. Interrupts, external interrupts. Now, in our programming, Paul, we use interrupts all the time. Sure. And that's what we do. So now here we only have two. So that tells you something. So now it changes the style of the program a little bit. Communication, serial and stream. That sounds familiar. Keyboard, mouse. Okay. So that's pretty much the language reference. Let's go back again to the slide deck, if you would.
Yeah, the thing that I like about the language reference and looking at that is that it doesn't seem like it's way out of what we're used to programming against. Obviously every environment has its specific things that you have to know about. The syntax is very specific to that environment, and you'll see that with the Arduino. But it's not like you're having to learn something brand new. So if you've done some procedural programming, you programmed in C# or C++, even JavaScript, all of this should look very familiar, and that's comforting, right? It's nice to know
that's a good thing.
Right in.
It's a good thing. Yep. Okay. So now we're going to talk about Visual Studio, right? Because we're using Visual Studio with an add-in, which is called Visual Micro. You can get free versions of both. So the Visual Micro requires that it not be the Express SKU, but there's trial versions of Visual Studio that you can use, and we're going to use. Well, actually, we have our own paid versions, but the trial versions will work just as well. So we're going to use those. We're going to jump right in, maybe, I think, and start showing Visual Studio.
And Visual Micro is a Visual Studio add-in, correct?
That is correct. It's an add-in, yep.
Which you can install from the Arduino site.
Yeah. So pop open. So we're popped open in Visual Studio here. I have it open. But Paul, could you just make sure that we're on track, that we didn't skip anything? Was this our next step?
It is our next step.
All right, perfect. All right, so here I am. What am I going to do? I am going to create a new program. What do we want to do, though, Paul? For our first demo, we're gonna rotate a servo.
Yes.
We are, and we're going to read a switch, I believe.
That's right.
All right, so we're gonna, a lot of times you'll see the blinking LED first demo, but we're jumping right in. We're jumping right in, Paul.
Yeah, I think you wanted to show a little bit of how the environment looks in Visual Studio, so let's do that first, and then we'll jump over to the first.
All right. So here we are, Visual Studio. I see now that I can select a Arduino board. Okay. I'm going to check the Arduino Uno. I'm going to see where it's configured. Hey, there it is. Great. That's what I want. Visual Studio, we have the menus up here for File. Let's say File, and let's say New, because we're going to create a new one. Nice enough here. We say a sketch project. That's great.
And all those options show up once you've installed Visual Micro, correct?
Correct.
Okay.
Yep. Visual Micro is the add-in that provides support for the Arduino systems. All right. So we can just call this test 05. I think that's a safe name. Say OK. And what do we get? All right. It takes a second. All right. So we see, OK, here's that setup we talked about. And loop. OK, very good. Now, we are going to add a couple lines up here, Paul. When I go up here, now I'm in a global scope. So that means that these variables I define up here are globally scoped, right? Which means they're accessible from anywhere. So I'm going to add a couple. I'm going to say, let's see. So we're doing, we're going to control servo, and that's controlled off a pin. So I'm going to say int pin servo. All right, great. I'm also going to say
before you keep going, can you make the font just a little bit bigger for our viewers? I think they might not be able to see that size.
Every time I open this up.
Yeah, that's perfect. Okay, great.
All right, very good. Thank you, Paul. All right, then we're going to do int, let's say servo speed, because we want this thing to, let's spell that with in the English language. You know what, Paul? We need something. We talked about the language reference. Arduino also provides us with a library. We didn't really talk about the libraries, but we have libraries. And we have a library that will help us with the servo motors. So we say include. You might be familiar with doing this in other programs. Say include now IntelliSense here with Visual Studio. Kind of nice, right? We see all the Arduino libraries. Now, it's a long list, Paul. You can kind of tell from looking at this. But if we start typing in servo, hey, look at that. Finds it for us. We hit the tab key, and we say, OK, there's the one we want. I scroll down, say that. All right, good to go. We see the color changes for us because it knows it's there. All right, and now we have our servo library.
Now, how did you know you needed the servo library?
Well, because I've done this before.
Yeah.
So no, but what you can do, let's switch back then. Let's switch back to the Arduino site.
Right.
And we see this thing up here, libraries. right? We're going to see some of the libraries.
And again, this all depends on what you want to do with your robot. So we knew that we were going to drive a servo, so we used the servo library to do that. And that's just becoming familiar with the environment and with the language.
All right, so let's see. So now there's a bunch of different libraries here. Now these libraries are written in C++. You might have seen the extension .h, right? Which is pretty standard. So C++, and you can write your own libraries. I guess that was what I was going to say, Paul. You can write your own. But they provide a bunch of them for you, and they also provide some of the third-party libraries available here that they think are really good and they've seen work well.
That is fantastic.
All right, so, Ethernet, we understand that. Liquid crystals, display of some kind. Here's servo, right? We know we want that one. You can do a different type of motor. We haven't talked about that yet. But let's go ahead. Let's look at servo since we're here.
Right, just to get a sense of what the library does, and then you can figure out whether you need it or not.
All right, here's the functions. Attach, I don't know what that does. I really do know what that does, but you guys don't know what that does. Write microseconds. So, okay, attach. I'm going to take a guess, Paul. I'm going to say attach helps us connect to the hardware.
Yeah,
I'm going to say write is, sending a message to it. Read is going to read from it. Attached and detached. I guess attached would tell you whether it is attached or not. And then detach would detach it after you've attached it, right? So anyway, a bunch of different things. They have some examples here. We're not going to look at those. We're going to switch back over to Visual Studio. So right before we do that, attach, write, microseconds. I'm going to have to remember these things, right, Paul? I got to remember it.
I think
you don't think
Visual Studio may help you.
Visual Studio.
We love Visual Studio.
All right, let's see. All right, let's go ahead and build this. I just want to make sure. I saw that these. Well, we'll try it without. We'll just see. Yeah. We'll see how good this is.
Throw caution to the wind. Why not?
Sometimes I build it at the beginning just to make sure my external references are really loaded.
I do that all the time.
Right. But let's try this. Let's say servo. All right, it found it, and it uses color. So now, but what do we do? What are we going to do here?
Hit the dot.
Let's build this project, Paul. Let's try that again.
Actually, you need to create an object, right? You have to instantiate an object first.
Oh, Paul, you're right. What am I doing?
That's why I'm here.
I was setting myself up to fail there. All right, servo. Right. Servo. My servo.
Now you're going to get all the...
Oh, good. All right. Now we have that. So now we have our pin for our servo. We have servo speed. I know that we want to have another one. Let's have int servo stop, because we do want to be able to stop it. And anything else, we got the pin, we got the speed, we're going to be able to stop. I think that's good for now. And so those are our variable types. Let's go into setup, because this is where we're going to configure these things. Let's say we called it my servo. Let's say my servo. Hey, there's our IntelliSense again. Select that now. There
you get all the fun
like
stuff.
You said, Paul, I was just confusing myself. All right, and we're going to attach. We can make sure that's selected, and tab to get that. And what do we attach? All right, again, it helps us out here, and we're going to use an int for the pin. It tells us we want our pin. So let's start typing pin, and we get pin mode, which we don't know what that is, but we see pin S is pin servo. That's our variable. We're going to use that one and put our semicolon there. Okay, so now we're attached to our servo. What else do we need to do? We need to assign some values to that pin. We didn't do that yet.
So the pin is actually the physical pin on the board.
That is the physical pin. Yeah. That is.
And so
it has a number.
The board is a number. All the pins have a number, and you just look at whatever number you plug your servo into, and that's how you attach. So it's all fairly self-explanatory, which is makes it really easy to get started.
So I'm signing it to pin 3, and I think that's what I'm attached to. We'll check it before we go. And we haven't really shown them a servo yet.
That's right.
So we'll take a quick second before we run this, and we'll just look at it real quick. So like you said, you got 3 wires coming off of your servo motor, right? One is the controller or signal wire, and then you got a positive and negative voltage. So so we have that. So all right, so we have a pin, and we are that's pretty good for setup. Pin attach. I don't think we need much more there. Let's move down into loop, and this is where we're going to do the controlling. let's set. You know what? We're gonna do another function too. We're gonna control it within another function. So let's say this. Let's get rid of this junk that I just did there. Delete that. Let's delete this. Let's come down here, and we haven't done this yet. But you're not limited to setup and loop.
Right.
You create your own functions, right? So this one is just going to be of type void. We're not going to return anything with this, so it's void, and we're going to call it run servo, and we're going to take a parameter. It's going to be an int, and we will call that speed, just SPD. Okay, and we come in here. All right. Now, down here, we're going to use this speed. We're going to move our servo, right? We're going to say my servo, because it was up in our global space,
That's
right? So now we know that.
It anywhere, yep.
And we're going to say dot, and we have this write microseconds. So we didn't look at these functions before, Paul, but I'll tell you a little bit about them.
Great.
Write microseconds provides us with a little bit more control. It takes a range in microseconds from, well, 1,500 microseconds is the middle, and that's usually a servo stopped at that point. Then plus and minus, say, about 1,000 off of that is going to go either rotation, angular rotation, 90 degrees plus and minus either way, whether you add or subtract. Now, we're using a continuous rotation servo. If we put wheels on a regular servo, it would just go 90 degrees back and forth. It would not go very far.
That's right.
We did not pick that. So, but for a continuous rotation servo, Paul, 1,500 is stopped.
Sure.
Instead of being in the middle of the movement range,
Got it.
it's stopped, and then if we go minus, it goes backwards. If we
So-
go
so-
positive, it goes forward, clockwise.
Seconds sounds like
counterclockwise.
a temporal thing, but it sounds like we're moving something in space, right? So why is it microseconds? It
Yeah,
sounds
you know
counterintuitive.
what? That comes down to the signal that the servo motors work with, this pulse width modulation. It is, as the name says, it's a pulse, and that pulse goes high for a certain amount
I
of time
see. Got it.
within its cycle. And so that duration, while it's high, it's getting positive voltage, and the longer that signal for some of these things, it'll interpret it different ways, but for the longer duration, it's going to go faster, right?
I see. Makes sense.
So you can do other things with it. With pulse width modulation, you can use it for setting voltage on an LED and make it light. You know, there's different things. There's things that you can do.
Right.
But what we're doing is extending that pulse longer.
Or
with
shorter. Okay,
or
that's-
shorter.
that's intuitive. That makes
Yeah, that is something. We're not going to cover everything today, Paul, but we'll try and make sure that we kind of explain. So thank you very much for that. All right. Now we're going to say speed, right? And now we've given it a speed. All right, not much else to do other than in our loop.
You need your semicolon there at the bottom. There.
All right, I make a lot of mistakes. That's why Paul makes the big bucks. He cuts.
I'm here for a reason, right, Chris?
Right. All right, so let's see. What did we do? We have this thing. It's called run servo, so we need to know that name. I'm just going to copy that up here. I'm going to say paste it back in. And I'm going to say here, I'm going to say, what did we say? Servo stopped? Stop. And did we assign a value to that, Paul?
We have not yet.
Whoops. I gave it the wrong one. Well, let's do this. We'll fix that. Since I gave it the wrong one, let's say servo speed equals servo stopped. All right, stop.
Got it.
Plus, let's say 200. That'll go a little bit fast, right? But we didn't assign a value to stop. That was something that we were missing here. So let's go back up into our setup, which is where we should do this. And we say servo stop equals 1,500. That's the middle of our range. All right. Now, Paul.
You need a semicolon again there, Chris, in the loop. There you go. Perfect. Now, will that loop just keep looping?
That loop. So what this will do.
Running over and over?
So we'll talk about that real quick.
The program
So in our global space at the top, happens once.
Yep.
We come down into setup, also happens once.
Correct.
Loop continuously runs and runs and runs. Now, in loop, we can call our other functions.
Right.
From our other functions, we could call other functions
That's right.
too.
Sure.
But loop is the thing that's cycling.
Got it.
Yeah.
So
All right. Now, let's build this thing. Oh, that's a fast mouse. Barry's got a fast mouse in here.
That's right.
All right. Did we get any errors? I don't see any.
No.
All right.
To me.
Let's see what happens when we run this thing. Let's just say debug. We'll just say run without debugging.
All right. Let's see what happens.
All right. There it goes, Paul. I see uploading is done, and there we go. First try. Okay. Very good. All right. So now we've gone through. We've set up our pin. We've created our servo object in software. We've attached that object to our physical servo. We've given it a speed. We've told it to go. That's great. That's great. Now, we still haven't read the switch, right?
Right.
So let's see. That's Paul, so that we don't have that sound going, I am going to just quickly rerun the program with our speed at 0. So I've removed the plus 200.
Yep.
I'm going to say debug and start without debugging. It's going to go out here. It's uploading the program. It's done. Now the servo should be stopped. So we don't have to hear it.
Now, why is it still moving a little bit? Can you?
Okay. Yeah. Okay. Let's see. It's turning just a little bit. That 1500 value, right? Servos. Actually, these continuous rotation servos. They come with a little adjustment to the potentiometer in them that you can zero. So you can physically zero out that 0 point, so it would be where it is supposed to be. So this one doesn't have it quite right. So we could adjust that 1500 to get it to stop, or we could physically adjust the servo, which is probably the best way to do it. So anyway, now our next step, right? We're most of the way through this demo, but we're going to do a little bit more. We are going to add another digital pin. We're going to read the switch, and it's set up off of pin 10. We are going to say int pin, we'll call it switch. And then down here, Paul, there's another little trick. I am going to switch over here real quick. I am going to go back to language reference. Just show you a little something here. As it's taken its time to get to a language reference. Here it is. We're going to do a digital read on this, right? So let's look at digital read real quick, because there's a bit of a trick here of what you have to do. In order to hold the switch at a position, we'd need a resistor to hold it at a signal otherwise, right? So what we see here, there's a little note in here somewhere. A note. If the pin isn't connected to anything, digital read can return either high or low. It can be random.
Got it.
Right? So we don't want random. So what we can do, and now I don't see it here, but I've seen other places. What we can do is, and I'm going to switch back over to Visual Studio.
And by the way, it looks like Visual Studio jumped your font size back down, so you bumped it up to 100.
Oh, those little rascals.
Yeah. There you go. Perfect.
All right. So okay. So we have our switch. But in setup, we're going to, so we go into this pin mode. Yep. Pin mode tells us how we're going to use the pin. So we say pin mode, cap lock, don't want that. Pin mode, we got the right one. Let's pick it. Tab, and we say pin mode, what do we need? Okay, we need the pin number, and then we need another value. And what we're going to do is we're going to say pin switch. Switch. I should have named it something different. Oh, geez, I got it again. All right. WITCH, comma, and now we're going to say high. All right. Okay, so now what we're doing is we're saying that this pin mode on switch 10, which is our digital read, is going to be set. Paul, again. I'm doing it wrong. All right. Pin mode, we're going to say input. We're going to say input. We're not going to say high, because I don't think it would understand what that meant. But we can say input. Now, instead of doing a digital read, we do a digital write. We do a digital write,
because
set
we're
it high.
switching the mode, so that switches the mode.
Yeah, the mode was for mode.
Got it. Of course, that makes perfect sense.
Okay, now digital. And it would give us the digital read here. Here it is. And we say here now, we want to say, did I say digital read, Paul? I did.
Yes.
But what we wanted is a digital write. We're going to do a digital read, but first we're going to do a digital write.
Because we're essentially setting the property.
Yeah, we're going to write to it. Now we have the two parameters. I was like, what did I type in? I see only one parameter there. I can't set it high. All right, we say, again, pin switch, comma, high. Now high is there. We do that. Now we have a good control on that pin. Now when we go to read the pin, okay, the pin is, let's do this. I'm just going to switch it to the setting that I think is off. And now we're going to come in here and we're going to say loop run servo with this particular speed. And let's do this. So we've said servo stop, but let's do something a little bit different. We're going to create another function down here. We're going to call this read switch, but we are not going to have it type void. We are going to give, this is going to be an int. We're going to return an int on this. We're going to say read switch. And we don't need to pass it in anything. We could pass it in a pin number if we wanted to make this more versatile, but we're not going to do that.
Yep.
Read switch. Okay. Now we do our digital read. R digital read. And now we say, of course, pin switch. And I'll just select that.
And that's another global that you set, correct?
Yep.
Perfect.
All right, so now we read digital switch. Now if switch, so we're holding it high. If it goes low, we want to do something different, right? So we're going to look at that. We're going to say if, hey, Paul, let's set a variable there. All right, let's do a local int. Because we got to assign this read to something, right? Int, let's say switch value, I don't know. Now let's say switch value equals this read. Okay, so now we have a switch value. We assign that the digital read off that pin, and now we say if switch
you don't have
value.
you don't have a C in your value, but that's okay. I just want to make sure they're consistent. It's with.
Yeah. Oh. Well, let's.
It's all.
I'm gonna fix it. T C C C.
All right, there you go.
C. All right, nice and easy. And we're going to say if it's equal to high. That's one possibility, right? Yep. It's either going to be high or low. If it's equal to high, then we want to change our speed. Let's say servo speed. Servo speed equals, and it's starting out high. We're holding it at high. Mm-hmm. We set it equal to 200 before, right? Mm-hmm. So we're going to say then servo speed equals 200. We'll just be consistent with what we had before. I'm going to do this because I'm going to have an else here as well. And so I'm going to move that in there. All right, put that in there, and then I'm going to say else. And we'll say else. Servo speed equals minus 200. So we're going to flip direction based on our switch.
In the opposite direction, yeah. And you can use that switch to turn the machine off and on if you wanted. We're using it to change direction, correct?
Yeah. You can do whatever you want, right? Sure. You read the switch, it has a value, you decide what you want to do with it. Yeah, it's very, very versatile, right? But we're just getting this concept of, holding, we're holding a pin high. We're setting pin mode. We're doing all kinds of things here, right? Yep. We're using pin mode to set whether it's input or output. Right. We're then doing digital read and digital write. All right, let's see what we got here.
Yeah,
we're returning servo speed. So up here we want to say, instead of servo speed equals stop, we want to say stop plus, let's do this. We'll do this a little bit differently. We'll say servo speed equals, what is it, read switch? What did we call that
I think
thing?
it's called read switch, yeah. IntelliSense will tell us, right?
I don't know about that.
Okay.
What was it, read switch? Yes, it will if we start with the right letter.
Yeah, that's right.
Read switch, and we get that. We did not pass it a parameter. So now, instead of saying this here, we need to add that 1500, right? So it's the servo stop plus
Right.
servo speed. Okay, so now we've kind of kept our code pretty much the same. We're setting servo speed off of read switch, and then we're adding our middle range to that before we run it. All right, I think we have most of what we need here. We've got our pin mode off of pin, and I am just going to look and see what pin number we assigned that. We did not assign it a pin number. We always got to give them the numbers. Pin switch, right, equals 10. All right, Paul, I think that is going to do it for us.
Right.
Let's see what happens.
If it compiles.
We'll rebuild that, see if we have any errors. We don't have anything yet. Let's try and go ahead and run without debugging. All right. Now, okay. I don't remember which way it was going before,
right.
Paul, but
if it switches them, you know
I'm going to pretend that that's the same way.
That's right.
And now, though, I'm going to come in here, I'm going to reach in there, and I'm going to flip that switch. Oh, and look at that, it's going the other direction. So that really is it. That's our lesson here, right? We packed a bunch of stuff in here, but we're controlling a servo motor.
That's right.
Didn't take much code, right,
Nope.
to do that. We're using the library. And then we're reading this digital pin, a switch, connected to a digital pin. We're reading that. We're getting the value. It's either high or low. We're using that high or low. We're checking it, and we're changing the direction of the servo. There we go.
And because the program's in a constant loop, it's going to constantly look for the value of that switch. So the reason that it's detecting that we made the change is because we're constantly reading the value in that loop function.
So if we switch it back, it's still running, right, Paul? So we switch it back. We'll just switch it a few times just to show, you know, it wasn't a trick.
That's right.
Right? It's running that way. It's running that way.
And because it's in that loop, it's constantly detecting the value.
And the loop is nice and quick. That's what you want. You want because you want the response to happen very quickly. So there we go.
That's it.
I think that concludes that demo, Paul.
Great. We just had one quick slide, just in review. We wanted to make sure that we talked about what we talk about what we talked about.
Right.
So remember, Arduino is the popular open source standard. Robotics hardware, you can get into it for very low cost, and it's fairly easy to program, as we tried to show you here. And then if you think about the programming model is very similar to other types of programming that you probably will have done. So it's not like you're having to learn anything new. You can get into this for very little money and very little time.
Yep. Very good. All right, Paul.
That was a lot of fun.
I think
Thanks,
that
Chris.
wraps up Module 2.
Module 2. Yes.
All right. We'll be back with Module 3.
3 in a bit.
All right.
Hi, and welcome back to Programming Robotic Systems with Visual Studio. I'm Paul Party. I'm here with Chris Howd, and we've been walking you through building these small robots and then programming them using the tools of Visual Studio. So we're going to jump right back in. We're going to actually start Module 3 by looking at how to build an actual Arduino robot using the Arduino boards. And we're going to walk you through the components of building this robot. So
we'll be doing the MS bug bot,
that's right,
that we demoed earlier.
You can see that guy right here. We showed this in Module 1. We just gave a quick demo of how he works, and we're going to show you the components of how to put them together and then do the programming so that he can actually walk around and bump into things. So as we get into this module, there's some things obviously that you want to consider as you're building this robot. the one thing that we did is we started, what did we want the robot to do?
Right.
So
always
design requirements.
figure that, right? That's going to define your hardware. So it's like, what do you want this thing to do? Do you want it to climb upstairs? Do you want it to make coffee? Do you want it to wander around bumping into stuff and changing direction?
That's right.
We picked one of those. Then you figure out what you want. Then you start working on your hardware list. You can pick your controller. You got to think about cost, though, right, Paul? This is, everybody has to think about cost,
That's
right? You could have a lot of money. You still should be thinking about your budget. And then you go through. You're going to need shields. You're going to need this. You're going to need that. What are your materials going to be? What do you have the tools that you'll need to make the parts? Those are the kinds of things you need to consider.
Yeah, so then that's just all goes into the design of the robot, what you need to do to get the robot to do what you want it to do. So we're gonna talk a little bit about that. We'll look at the hardware itself and show you a demo of how the hardware works. We have a little kind of test bench here, which will show you how things are put together. We're going to do some diagnostics. So as you'll see, there's some complexity in making sure that the wheels are calibrated properly and that the bump sensors work and all the rest of it. So we'll show you how we put those together using kind of these incremental test benches, and we'll walk you through them. And we'll do 3 different demos, and then we'll pull it all together at the end and show you how it works in an integrated way in our MS bump bot. So that's what the module is going to look like. All right, so when you consider your design requirements, Chris and I were just talking about that a little bit. Again, what do you want it to do? What are your budget constraints? What hardware will you need? One thing we didn't talk about earlier was tools. So you're going to obviously need a bunch of tools to put these things together. The robots that we're showing you aren't terribly complex in terms of needing a lot of tools, but you will need certain things. Chris will talk about that as he talks about the assembly of these robots. One of the things that we actually used pretty heavily was a 3D printer, which is not on everybody's workbench, but it does help if you're needing to make a part. The robots that we're using use plexiglass mainly, so that's how we built the frame, and the legs of the the legs of the spider aren't plexiglass. But Chris will talk about the materials there. But there's lots of materials you can use. A 3D printer allows you to kind of put those things together.
The main thing is think about what you're trying to achieve, pick your materials within your budget. And don't overdo it. Don't overthink it.
That's right. All right, so let's just jump right into the BugBot device itself. We'll look at the MS BugBot hardware.
All right, sure. Okay, so we picked plexiglass. One of the reasons really was that we wanted to be able to see the parts through it for this series, right? So then we're using continuous rotation servo motors. We've already seen how to use those. It's pretty reasonable cost. And then we just use these wheels, right? You could get wheels that attach. That was pretty cheap too, and they have a caster in the front. For our electronics, we have an Arduino Uno board. We have the bump sensor switches, and then we have some wire and some glue and some different things like that. We have a nickel metal hydride battery, and we actually have 2 of them. But that's it. That's our materials. Short and sweet.
All right, let's talk about some of the specifics in actually putting this thing together.
Right. Okay. So now we've seen how we have one wheel and we can turn it forward and backwards. Might have seen a little bit. I can't remember, Paul. Did we see that servo kind of turn in a little bit?
We
talked about the center speed. So you want it now that we have 2 wheels. We want them balanced in their speed, right? Because if it's not balanced, it's going to turn at a funny angle, right? It's going to go. It's going to go in an arc instead of straight.
Demo,
we did. We saw that was not calibrated correctly. So what do we want to do? We need to balance those. We're going to go forward a little bit faster, and we're going to go backwards. That's a personal choice. We need to be able to control the motors independently. So we want to balance the speed, but we also want to be able to have one wheel going faster than the other so that it does turn, or we could make one wheel go backwards while the other's going forward so that it spins in a circle, right? So those are the kinds of things we want with our wheels. Code structure, right? We already looked at a little bit of that too, Paul. When we were building our other routine, we separated out the function for wheel speed into its own routine.
That's right.
We're going to do that kind of thing again. What we'll do is we'll control our wheels with their functions, and then we'll think about the robot as an abstraction layer above that, right? So we'll say, okay, we're going to use these wheels, but if we want to spin the robot counterclockwise, we'll have a function for that, and then we'll call the wheel speeds from there. So we'll send one wheel in reverse and one wheel forward if we want it to spin.
That's right.
Flip it around if we want to spin the other way. Same for forward and reverse. So we'll think about our robot as an entity, and we'll use these little functions calls to control it.
Great. All right, let's switch to the demo then, and we'll talk about using the diagnostics tools to manage wheel speed.
All right, so here we are in Visual Studio, and we have this already set up a little bit here for us. We have 2 servo motors, right? 2 servo objects. We've already got our library set up.
And again, we looked at how to do that in Module 2.
We did.
So we're using essentially the same servo library, and then we have a wire library as well.
Right. So we have an integer for the servo control pin for the left servo and the right servo. We have the speed left, forward, and right, forward, back, and stop. So we have our different speeds set up. We're going to have a little Boolean here that tells us whether it's in diagnostics mode, because as you're working on your robot, it's nice to have a diagnostics mode that you can go into rather than have it go into the live robot mode. That way you can check out your stuff, your wheel speeds, and get those all calibrated in a routine. You can leave it there because you might need it again. And then you have it and you can work in that area. Right? It's just a good practice to be in.
That's right.
So we have, back to the code, we have a Boolean for that. And then we go into setup, all right? Well, we got our pin settings, and then we're attaching our motors. This is all the same stuff that we did before. Now we have our speeds, right? You can see we're saying our forward speed is a little bit bigger, about twice as big as our backward speed like we wanted. And we set diagnostics mode true, so we're going to go straight in. Over here, you can see some comments. See, I ran this code before. To get these balanced out, we're actually going to have to tweak one value up. The left servo, we'll tweak that speed up to 109, and then we keep the other at 100. And then for the reverse speed, we're going, the other one is going up. That was the experience that I had when I wrote this the first time. These things drift a little bit in their values, so we might see something a little bit different. Then we have our loop, right? And we have it set up here so that we can stop the robot, we can run it forward, and we can run it backwards. And then down here, we're controlling our wheels independently, and we'll be calling those routines, right? And then here's forward, backward, and stop. All right, so that is the code. Let's go ahead and run this. We're going to say stop first, just to see what it's looking like. That's where we'll balance them, right?
Sure.
Because when it's stopped, they should both be stopped. And we'll see if one of them's turning or both of them are turning a little bit. We're kind of expecting, I don't remember. I think I must have balanced these out because we didn't say adjust one of the 1500s. But let's see what happens. All right. Let's see where we are. And we'll say debug. And we'll start without debugging. Are we connected, Paul?
We are plugged in.
All right. Let's see what we get. We're uploading. Done uploading. And guess what? You need to turn the power on these things, oddly enough. Okay, so we're actually seeing both of them turn a little bit in opposite directions. Mm-hmm. Paul, you know what? I am going to say that's okay with me for right now.
Okay.
We could go up here. Well, we'll do it real quick. We'll just try and adjust one of these. We'll say that this one, we're going to say, is 1490. We'll see whether it goes the right way or not.
So those are supposed to be in stop position.
We'll see. We'll switch back now to the little guy. Oh, we got him going there. Let's go ahead and say run that again. Yes, it should be stopped, and we'll see whether one of them actually speeds up or whether it stops.
Oh, there we go. A little closer.
So anyways, that's the idea of what you do, right? You adjust that. We could adjust it in hardware. We talked about this before. These servo motors have a little spot on them. This guy's probably blocked off. I'm gonna tip it up towards the camera, and you'll see it, the little areas. So do we have a good enough view to see those two little holes? I don't know, maybe not. But there's a little hole right here. There's a screw in there. There's a potentiometer, and you can adjust your zero position. That's good enough. So one of them seems to have stopped. We adjusted that correctly. You use the same technique for the other one. But we're going to keep moving here. And we're going to say, okay, stop, fine, we kind of get that. Let's check forward. And again, right, we want the speeds to balance. So we're going to say, I'm going to do a Control F5. That's same thing as using the menu for run without debugging. Now they're moving. Well, we have one end that's a little bit silvery. Looks like maybe one of them is catching up to the other one and passing. It's a little bit faster. Let's just go up real quick. Let's try and see if it stayed at that value. We're going to put in a 109 there. Let me do, I would think about adjusting that 0.2 back to 1500.
Yeah.
Just in case, but I'm not going to do it. We'll just try it because I think I had them both stopped before. We're going to rerun this, Control F5. It's going to upload the program. Now it has the new value in it. And maybe they're in better sync. I can't really tell for sure.
A little bit better, yeah.
But you kind of get the idea, right? That's the way we do that. It's good to have them balanced because now, right, if they're close, at least it'll go pretty straight.
That's right.
And that's what we're trying to achieve. And you do the same thing for reversed, and then once you've gotten that done, you're done with your calibration piece, right? And you can do it for different speeds too. If you need your robot to be running at a bunch of different speeds, then you can calibrate the wheels for each of those speeds, and you'll be all set, and you can go forward and nice and straight at all these different speeds.
Does the cost of the motor improve or decrease the calibration and the ability of the motor to operate in sync with another motor? Have you noticed that?
You know, Paul, with these servo motors, I've purchased a few different brands of continuous rotation servos, and I think they all need a little bit of adjustment.
Yep.
But they're also relatively expensive. I haven't purchased ones that are super expensive.
Sure.
So those I would expect are probably going to be a little bit better behaved.
Yeah.
But I think I've run this, Paul, and maybe we switched directions.
Yes.
So there was an adjustment indicated up here that we could switch this value up a little bit. We'll try that. 65 here, and we'll rerun that again. It's going to stop while it's loading. It's going again. And now we should have them balanced in forward and reverse.
Yeah.
And that is how you do it.
Got it. Now, is that number applying to both motors? The right servo speed right, I see. Servo speed right and servo speed left, I see. So you have them separately.
So here's another thing we should point out, right? We've mounted these two servos so that the wheels are pointed outside the outside edge of the vehicle, right? So now they're in different orientations.
Yes.
So you can see we were saying plus to go in reverse on one, and it's because they're going the opposite directions, right, from their own orientation. Sure. So you do have to switch that around. It's just another thing to think about.
Yep.
But that does finish us up with this demo.
That's right. That's wheel speed diagnostics. So maybe we can...
I'm going to unplug this so we don't have to hear that.
Yep. All right, what we're going to do next is look at the bump sensor. So if you'll remember from the demo that we did in the first module, the little bump bot actually has bump sensors to indicate when it hits a wall. And when it detects that it has hit a wall, it will stop, and then it will reverse direction, spin a little bit, to try to get away from the wall. So the bump sensors is actually an indicator that the robot has on it, sends a signal to the board. The board then, you can have the program adjust to that signal that's being sent to the board. So we're going to show you how that works now.
All right.
So
we have a slide we're going to talk to here?
Right there.
All right, here we go. Sensors and pins, configure them. We've done a lot of that, Paul.
Sure.
We have. We've already done that. But basically, you just tell it what pin you're using. It's a digital pin because we're gonna read it. We hold it high. Remember how we did that? We did the digital write to hold it high. That uses the internal resistor on the Arduino board to hold it up high until it gets pulled to low, pulled to ground, right? Which the switch does. And
again, if you missed that or you're just joining us, check Module 2 out. We talk about all those things in Module 2 when we show you how to program that. So check that out.
All right, so Paul, all I need to do here, so we got this new little guy, right, here. And so he's got the servo in front. That servo's going to run until we touch one of these switches. That should momentarily stop that servo as we touch each one of these. We're wired up to 4 of the digital pins, grounded, and we have a wire for the servo and some power. So I am going to plug in the board to my PC so that we can upload that program. If this little guy, it looks like we're running off of the power of the power supply off the USB. So it's not, I wouldn't say that's a best practice for a servo, but we can get away with it here because we just have one, and we're not going to pull too much power. All right, I am going to switch. I have another Visual Studio project open here. Let's look at the code a little bit of what we're doing. Again, we have the servo, so we needed that. Otherwise, for the switches, we don't need that. But we could have used a light, Paul, but in here it's hard to see the lights. So we're going to use a servo to see that the switches are working. We have a pin for each of the switches. So this is front left, to understand my code here. Front left, front right, back left, back right. And then we have a sensor value, because we're going to read the value off of the pin. And then we have a robot state, which, Paul, I don't remember what that is. We're going to have to see down lower in our code. Yeah. We have a servo pin, servo speed, and we say my servo again. The servo's on pin 11. We attach the servo like we did before. We set the speed at 200, and we do a write, and we start it moving right off the bat, right? So it's moving as soon as setup runs. Then we set the values on our pins, and we use pin mode to say their inputs. We hold them high. All right, in our loop, we say robot state equals bump, read bump sensors. So our robot state comes back from our function, which is going to read those sensors. And then we're going to run the servo, and the servo is going to be running at the stop speed of 1500 plus the servo speed, which was 200, times robot state. So I'm thinking robot state is going to be a 0 or a 1, Paul.
Yeah, that's right.
I'm guessing. Let's see what we got. We got an int from read bump sensors. We read the values off each pin, right? They're held high, which is going to be a 1, until they get pulled to ground, which is going to be 0. So we're looking at if the value of any of these sensors is low, return low, otherwise return high. So that's pretty,
switch the direction of the motor.
Pretty simple. It's going to stop it.
Oh, stop it. Got it.
Right. If it gets a low, then it's going to return a 0. We're going to multiply.
Oh, that's right.
Right, by a 0. And so we should be stopped. All right. So we're plugged in there. Let's try to build and run this guy. Rebuild solution. All right. And it's built without an error, which is always a good sign, especially, when I'm writing this code. It's uploading, and okay. All right, so now it's turning. This is what we expected, right? We told it to, in setup, we told it to start turning. And we're holding these pins high. Go ahead and, and hold it. So as long as you're holding that, then it stops. Yeah. And then the other pins would work the exact same way. I mean, if you can reach one here.
Go ahead and do it.
So each of these pins is wired apparently correctly. All right, so that's the whole deal there, right? We got each one of these things. So what we've done a little bit differently than last time, in our previous module, we talked about, we used a different kind of switch, right? It's a momentary switch. This is more like what we use in our MS BugBot, because when it bumps into a wall, as long as it's on that wall, that switch has a value, right? And we're going to do something. We pause, right? And then we back away, right? As soon as it backs off, that switch goes back, right? It's not permanently stuck there, right? Because otherwise it would stop all the time. It wouldn't need to run into anything. All right, so that's how that works, and that demo is also complete.
That's right. So now that's how you set up the sensors. Now what we're going to do is bring it all together and show you how both of these concepts, the wheel concepts that we showed you earlier and the sensor concepts, work together to form this MS BugBot robot. All right, so we'll pull it all together in code.
All right, so so we're pulling it all together in code. What does that mean? Well, right now we can read the switches, we can move the motors, but how do we decide to do anything, right? And that's what we're doing now. That's right. We're adding all that logic that says, okay, I want to be able to spin 360 degrees, or I want to spin counterclockwise for half a second, or I want to do this, I want to do that, and if you write your code smart enough, right, then you won't get stuck in a corner, right? Because this guy's going to go into a spot and it's going to try and back up, basically, right? But it needs to turn a certain way. So depending on which of the sensors is up against the wall, it's going to take that into account as it goes. It's also going to look at how much time has gone by since it's trying to maneuver out of that position. So if it's like it moves, it hits its front right side bumper, and it starts backing out a little bit to the right, and it hits its rear right side bumper, it's like, oh man, it thinks I'm in a corner. I need to figure out another way, and maybe it spins or does something. So those are the kinds of things you need to think about. We are going to move to the Studio B, to the pit, and we are going to look at that.
The bug bot on the loose.
All right, very good. Let's do it. Welcome back. Here we are in the pit. We are demoing the MS Bug Bot, and let's let it go. Going to turn this bad boy on, see which direction he chooses to go. I'm guessing kind of forward. Let's see how he does. All right. Now you can see he is turning a little bit as he goes, and that is because those servos are not bounced. We talked about that, but we did not fix it in our code as we should have. He's going to wait there for a second. He's going to say, all right, I need to back up. I've touched this servo, this sensor, and uh-oh. All right, we were talking about this just a minute ago. These walls are a little bit bouncy, and so if he runs into a position and gets a little bit of bounce back, the sensor releases. So we're going to try that again. And he should then back up, turning a little bit, and pick a new direction. He's going to go out here and makes contact with another wall. He's going to do the same kind of thing. He's going to say, all right, this time I ran into this. I'm going to move a little bit differently. He's moving backwards a little bit slower than he goes forward. And he's stuck in a loop. This code needs work. I expect all of you people out there building robots to do a better job than we did. All right, that is the MS Bug Bot. We will meet you back for Module 4.
Hi, and welcome back to Programming Robotic Systems with Visual Studio. I'm Paul Party, and I'm here with Chris Howd.
Oh.
Chris and I are going to continue to talk about how we build these really cool robots. We've been talking about continuous motors and robots that use continuous motors, and now we're going to focus on a robotic arm, which uses a different type of motor. Chris will kind of explain how this motor differs from what we've been showing you in the first 3 modules. So let me just give you a quick overview of what we're going to do in this module, and we'll talk a little bit about how we're going to build this robot. We're going to talk about what we call the MS Guard Bot, which is essentially a robotic arm. It does have wheels. You'll see later in the demo that it can roll around. We're going to actually have it do some cool stuff in our demo. But we're going to show you how we built this robotic arm and what's involved in doing that. Working with a robotic arm is a little bit different than working with a continuous rotation motor that you saw in the first robot that we built. And you'll see that you have to really account for how you position the arm, how you calibrate. You want to make sure that you're thinking about a lot of different aspects when you build a robot like this. So Chris will walk us through some of those aspects. We'll look at the code involved in how you control the arm. There's also something we're going to talk about a little bit later, and that's making sure that the arm movements are smooth. You'll notice when we get to the demo, you'll see how the robot actually works, but if you have the arm swinging too dramatically, it could cause problems for the motors, it could cause problems for the robot. So we're going to talk a little bit about how you can account for smooth arm movements in code using the motors that we're going to be using in this robot. And then we'll go into the demo and we'll show you how it all works like we have been doing with the past 3 modules. So I'm going to turn it over to Chris. We're going to talk a little bit about design considerations and constraints, and then we'll get into the specifics of how the arm was built.
All right, thanks, Paul. So, like you said, we instead of working with a continuous rotation servo, now we're working with a servo that's going to rotate through a full path of 180 degrees. So you can think of it as plus and minus 30 degrees, or plus and minus 30, plus and minus 30, plus and minus 90 degrees to get to 180. And we're dealing with robotic arm, right? So the first thing you need to do is you need to think about, what is this arm going to be used for? Is it going to be used to pick something up? Is it going to be used to move something from one location to another? How carefully does it have to move it? What is the material you're using? That kind of thing. So that's your first step, right? Is how is it going to be used? And then you need, again, like we talked about before, you need to think about your budget. Because if you let's say you have, I want 7 degrees of freedom in this arm because I want to curl it around and underneath something. But if you could get by with 3 degrees of freedom, so 3 motors, then you can do it a lot cheaper, right? So you need to think about your budget, what you need to do, and balance it with what you can afford to do. And then again, how is it going to be attached, right? Maybe you want to be able to swap out multiple arms. Maybe you have a robot that can use 3 different arm types, and you want to be able to swap it out. So how are you going to mount this thing? Do you fix mount it? Do you, maybe get slap in and slap out? If it breaks, you need to be able to replace it. So even if it's in a fixed mount position, you want to be able to take it off in order to repair. And then special hardware requirements, right? Is the load that the arm is going to be lifting or moving, or is it going to be heavy out on the end? And so then you have some mass out there. Do you need to use a special material for your arm, or can you get by with just about anything? So you have material requirements, and then the tools you need to manufacture your arm is the last thing. So that's pretty much it. I think then now we're going to talk just a little bit about what we did with our arm. So if we flip on to that next slide.
Actually, before we go to the next slide, one of the things that you had just mentioned is what's the arm going to be used for? Now we called our robot the MS GuardBot. What's our robot going to be used for?
Yeah, so for us, the arm is just going to be used to turn off this other robot, right? We talked about it when we showed the 3 robots in Module 1. We talked about how this one, it's just going to swing its arm from side to side, and it's going to turn off another robot. So that's what we're doing. So our primary concerns were the length of the arm. We didn't want it to be too heavy, but we didn't really have a material constraint on us. So we ended up, as we'll see here in a second, we ended up using plexiglass. We wanted the arm to extend out a certain distance out in front of the robot, and we didn't have to worry about the torque on the motors because the plexiglass is lightweight enough that we didn't have to worry too much. We ended up with using a pretty good torque motor, but that was just because we knew that we had the length of the arm, and we wanted to make sure that we were moving the way we wanted to without straining the servo motors.
What does high torque mean, Chris?
It's going to be a little bit slower, and it's going to be able to move pretty fast. The weight of the arm is not going to affect the servo's ability to move. Good. So high torque, big load, right? Lots of force. Okay. Slower moving, usually, because the gear ratio is going to be a little bit different. So with that a larger gear ratio, you'll get more force at a lower speed. So that's basically what it is. So so we ended up with the plexiglass arm, a standard servo, high torque. So the size of the servo motor is like that 50 gram or whatever the standard size is. And
then how did we mount this arm?
Yeah, so we're fixed, right? We are mounted on top. I don't know if we have a shot, but basically we just we mounted it on top in a way that we could get it off if we needed to replace it. So, but we didn't have to think too much about that. So we were lucky, right?
Yeah, great.
Simple design, and just the two motions, right? It can rotate and up and down.
That's great. So we've got a little bit of discussion here about how we actually put the robot together. Let's talk now about the positioning and calibration. What was involved in thinking about how we wanted to position the arm and then calibrating the arm so that it would function properly? Yeah.
So positioning, right? What you want to do is you want to have a position that makes sense for your robot, right? Whether it's an arm or attached to a robot, and you do need to think about how it's going to be attached when you're thinking about positioning. What is this home position? What is the natural position for it? The default position for it, right? For us, we knew we had an open container, right? So a default position of up was good for us, and forward. It didn't matter whether it was forward, left, or right, but we chose to be forward. It's kind of in that middle position, right? We can flip backwards, but we don't use that backwards flip. We move down. And then side to side is all we're doing.
And so when you turn the robot on, you want the robot to go to that home position? Is that essentially the idea?
Yeah.
So you need to know where that is.
Yeah, because you don't want it to swing out to someplace. Right. For us, it's in an enclosure, so if it started swinging side to side or it did one of these things by default, then it's going to be banging into stuff, right? So we didn't want that. So you just think about those things. What is the natural position? If you're making a robot arm that is actually going to be attached to like a humanoid robot, you probably want the home position or the default position to be arms at the side, right? Or legs are in a relaxed position, whether it's an arm or a leg. But yeah, just think about what you want. Set it up there. You still have your 180 degrees of motion if you want it, right?
But then you suggest that we also talk about the min and the max range, right? So for our robot, we have a min and a max. We're not going to use the full range of that robot, so we actually selected what range we wanted it to have.
Yeah, so if you have an obstruction that you have to worry about in the space that you're working in, you need to think about that. And so like you say, we're not using the full forward and back range, right? We're stopping because we have sensors on the robot that we don't want to bang into. So we could actually move it further down and further back than what we're allowing it to move. Right?
And it's 90 degrees left and right, and then 85 forward and back, correct?
Yep. So that is what we have. Now, some of the other things you need to think about is in terms of calibration is the speed at which it's moving, right? So we have our own considerations here. Because the arm is pretty long, we didn't want it to swing too fast, but at the same time we wanted it to swing pretty quick, right? So it's some trade-offs there, but we didn't really have specific requirements for our arm. It's just swinging back and forth. It's not moving something. So it's more important when you are going to be moving something, and that's what our demo is going to show, right? So if you're moving something from side to side or you're carrying a heavy load, you don't want to just snap it to one spot because it's going to put a lot of stress on the servo motor to either stop or get started, trying to move quickly. So that's important. You always have to keep that in mind, and our little demo will kind of show that. Now, with a servo motor, we end up doing little steps, right? There's different ways that you can do it, but with using the library that we're using, the simplest thing was to make stepped movements and understand the timing of the steps. So based on the distance that we're moving, the speed of our servo, we wait just enough time before we give it the next movement position. We do these steps. So it looks pretty smooth, but it's actually stepped. And we'll go through the code here in just a little bit and talk about that. But the idea is, don't snap it, right, if you can't in your situation. And in our demo, we have just a really simple little thing where our payload, right, the thing that we're moving, is in an open container. In this case, it's a little spoon, right? But we're going to move it in a way that we don't want it to fall out, right? You assume that your robot is going to be moving a liquid or something like that, or a powder or something from one position to another. You don't want it flying out of the container that it's in, and that's what we're going to demo is that benefit.
All right, let's do that. Why don't we go to the demo and we'll show how that works, and then we can talk a little bit about the code.
Okay, very good. So I have Visual Studio open here. And let me adjust the size of that a little bit. I think that's going to help. So we're going to set up the servos in the same way that we did before. So we have a pin assigned to the servo, so that we give it the motion that we want. We are going to be, in this case, we are not going to really use the up-down, because then we would be throwing our little payload across the room at Barry, and he would get mad at us probably. But we're going to be moving left and right. So we have, as we talked about, we have this min and max position, and we're just up in our defining our variables area. We move down through here, so we're using these pins. We attach the servo in the same way that we did before. We set up our home and min and max positions. And then we start sending commands. So in our setup, as we saw that setup loop in our other modules, in our setup, we're defining all our variables and we're moving into that home position that we have. And then in our loop, we're going to demo just the quick move, the default, just move to the position, and then we're also going to demo the step move. And hopefully, Paul, we're going to actually retain our payload within the little spoon in the stepped move. And that is pretty much it. We call these full range, so we have the functions set up, and we just call these different ones. We don't have to really look too much at that. I'll show you real quick. It's going to do its moves, and it's going to pause for a little while, and then it's going to move again. So you kind of get the idea, and it does the same motion sequence in both the full range move demo and the step move demo. So we're going to start it out with the full range moves. So let's go ahead and uncomment these lines.
And if you're just joining us for this module, we talk about a little bit how to set up your Visual Studio project, how to include the libraries, how to work with the code in modules 1 and 2. So if you're interested in that, please go back and review.
Yep. All right, so I will put our little metal part in there. And I think camera position looks pretty good there, so let's go ahead and start without debugging. All right, well, so that went pretty quick. Threw our little thing out of the way. It's going to go through that motion again, and it will just keep doing that in that loop, right? So see it do it again here. Yeah. So it falls out. So we get the idea there, right? Now what I'm going to do is I'm going to comment those lines back out again. I am just going to go ahead and send that out. Well, I was thinking, Paul, I would send out the updated code so that it stops. But I think what I'll do is I will just go ahead and uncomment these and send it out, so it'll go right into it.
Now the idea here is that once you update the code, it's going to move a little bit more slowly in a stepped manner, and that will control the arm movement and hopefully keep the payload in the arm.
Right, and at the same time, we didn't want it to appear too stepped, right? Yes. We don't want it to slow down too much because we want to continue to be able to move our payload from one position to the next, right? But we didn't want to do it fast enough that it caused a problem, right? So we'll see what happens here. It's loading up that code, and with any luck, it will stay in. Just barely, right?
That's pretty good.
So we kept it moving pretty fast. You don't really see the steps occurring, but you can kind of maybe hear the difference just a little bit.
Oh, yes, totally.
Just a little bit of a difference, but it looks pretty much the same. So we achieved our goal of slowing it down enough, smoothing it out enough with this stepped motion that we were able to keep it in place.
That's pretty cool.
There we go. And that, Paul, is pretty much it for our discussion of robotic arms, right? And like we say, we're going to use an arm on the MS GuardBot, right?
That's right, yeah. So a lot of the principles that we talked about here are fundamental principles that we're going to use in a more advanced way when we talk about building out that arm and how the arm ought to work. But it's the same essential principles, and the code is essentially the same structure. Thanks, Chris.
Yep, very good. I think that that pretty much does it.
That wraps it up for this module.
Right.
We'll see you,
we will
see you in module 5.
Be right back.
Hi, and welcome back to Programming Robotic Systems with Visual Studio. I'm Paul Party, and I'm here with Chris Howd.
Hello.
We've been spending the last 4 modules talking about building a couple of robots, and we've been slowly incrementing our educational program here to talk to you about different types of motors, different types of sensors, and we're going to continue to expand on that in Module 5. In Module 5, we've titled it Integrating Advanced Sensors and Shields. We've talked a little bit about shields already. So we've introduced shields to you. We showed you a website where you can buy different types of shields. And in this module, we're we're going to show you how to integrate those shields. You can use shields in a variety of ways, and they really do help so that you can isolate components, you can add more power, you can use bigger motors, and shields help with all that. We're also going to show you some really cool sensors. There's a wide variety of sensors out there that do all sorts of things, from taking temperature readings to doing depth readings. We'll show you again another website where you can buy a bunch of different sensors to accomplish whatever task that you'd want to do. So just in terms of what we're going to show you in the module, I'll give just a quick overview of what we're going to cover. As we've been doing, we're going to talk to you a little bit about design considerations for the robots that you need to build, particularly when you're thinking about sensor types and these shields. You have to think a lot more carefully, obviously, as you extend the capabilities of your robot. So we want to talk through some of this in terms of the considerations that you need to make. We'll show you some sensors, we'll show you some shields, and talk a little bit about where you can purchase these things and the types of options that you have. And then we'll do some demos. We'll show you how the sensors work, and we'll show you how a gear motor works. We're going to do this in very isolated demo robots, and then we're going to use the concepts and essentially these kind of fundamental principles as we build our larger robots, which we've been introducing in the past modules. So this is going to really help us get to that next stage of our robotics program and our robotic systems, and show you how you can start to integrate some really cool features into the robots that you will build. So let's just move into that. As we think about using sensors and shields, let's talk a little bit about some of the design considerations that you need to have as you think about pulling these things together into a functional robot.
Yeah. All right. So far, Paul, we've talked about kind of physical design considerations of more the structure of the robot a lot of times. Some with the servo motors, maybe a little bit with the sensors, not so much. But now we're really going to start talking about, your sensors. So they're reading something. These are your inputs, right? And some of the sensors are going to be line of sight sensors. So they're going to need a clear view. You might be positioning them, rotating them, right? As for our GuardBot, MS GuardBot robot, we move the rangefinders. We position them 180 degrees, right, in different directions. So they need a clear line of sight as they move. So they have to be positioned appropriately for that. But you also have to think about your design considerations for where your wiring is going to go, right? So you have electronics now that you're having to deal with, more electronics that you're having to deal with. The MS GuardBot, if you've seen some of the previous videos, you can see there's a lot going on. We have 5 servo motors, we have 3 rangefinder sensors, we have 4 gear motors. So there's a lot of wiring, and then we have 3 different batteries, right? So there's a lot going on there, and you have to think about where are you going to route the electronics, and you can't bury it too deep because you might need to replace it, right? So there's a lot to think about as you're designing your robot. With all these different sensors and things, and if you have shields on there, you're going to have to be able to pull the shield out if something goes wrong with the shield, and now you have to, all these different things, right? So it gets pretty complicated when you have a lot going on. So you have to think about it, do it right, and maybe it's not the first iteration where you get it right, but that's okay too, right?
I was going to ask you that. Are you a pencil and paper guy where you'll kind of draw everything out, or do you like to trial and error? Do you like to try to put it together, see if it's going to work, and then pull it apart if it's not working properly?
Paul, with the wiring, a lot of times I'll leave my wires a little bit long, and then I'll be able to cut them and resolder if I have to. But leaving it a little bit long gives me that leeway to see where I want to route it in the end. I'm not saying I leave it a foot long and it's all coiled up somewhere or whatever, but leaving it a little bit of slack in case you need to move it into a different position sometimes is good. So I will do that, but I do try to think about how I'm going to have it laid out and get it close to right the first time if I can.
I also noticed that on the robots that you build, you have wire ties in certain places, and you also use some hot glue to attach wires in certain places so they don't get in the way. I think it's a really good idea to have those fasteners available, whether it's glue or whether it's a tie-off, just so that you can kind of keep things organized and your robot looks a little bit better at the end too.
Yeah, and the other thing you can do with tie-downs is you can keep your power lines more separated from your signal lines so you don't get any interference. A lot of these are shielded, but some of them aren't, so you want to keep things isolated in an appropriate way as well. So having tie downs, like you say, Paul, that's a good thing to do.
Yep. All right, so we introduced shields in the past. We're going to go back to shields now and talk a little bit about how they work, and it's particularly as we think about integrating them into a more functional robot. We want to talk a little bit about why you would use these, and then what some of your options are. So Chris, why would we use shields in a robot? What do they accomplish? We talked about this a little bit before.
Yeah, and you mentioned the biggies, Paul. Is you're going to isolate your electronics. You're going to extend the functionality of your main microprocessor board. So our Arduino boards come with a certain amount of functionality on them that keeps the price down. We talked about this in some of these previous sessions. But those are the biggies, right? It provides a lot more power. We're gonna switch from using just standard servo motors, and we're gonna start using these bigger, well, not really bigger, but we're gonna use some DC motors, which will pull more current. And that's one of the other things the Shield does, right? Is it isolates that power supply, so we can run. I think these. The board that we're going to be using allows up to 2 amps, which the Arduino boards maybe give you 50, 100 milliamps or something like that. So it's, things that you couldn't possibly do with just the Arduino board, the Shield enables you to do. And it isolates the systems at the same time. So it's a big deal.
And now does the Arduino board expose the functionality of the Shield to code? So as you're writing your code, you can see what the Shield will provide, and it works as one unit, correct?
Yeah, and there's 2 different ways that the shields will connect usually. Some of them are just pin plugins. They'll plug in right on top of the Arduino boards. We showed the mounting pins for that previously, and we could probably show them again. I think you have a couple of boards.
Is this the one?
So it's got little headers on there. That's a shield that has headers on it, so that and they're stackable, right? So you could add this shield to the Arduino board, and then you could stack another shield on top of this shield. So it shows up a little bit. But anyway, so that's pin stackable, but then they have another receiver transmitter pins on these Arduino boards that follow a protocol. I don't really recall which protocol it's using, but then you can, with 2 pins, you can connect to a shield. And we do that in our MS Spider bot, where we have 2 16-channel servo motors, because we have 24 servos on the Spider bot, and we're using we have 22 servos on it. We're using 24 of the 32. I don't know what I said.
Yeah.
Anyway, we have 32 available. We're using 24.
Yeah, that's good.
So those are the 2 different ways of interfacing. You could either pin plug it in, or you can use these receiver transmitter pins to communicate with the board.
So again, the big takeaway is that when you use shields, you extend the functionality of your robot, but it does function as a single unit, which is really nice. So you can get all the functionality exposed for your code, and then you can program against those shields as well as the original Arduino board. So now we talked a little bit about shields. Let's move on to sensors. This is where things get really exciting, and this is where you can really extend the power of your robot to do a bunch of different things. So we're going to talk a little bit about sensors. We'll show you a website in just a moment, and I'll hold up some sensors and show you some of what they look like. But talk a little bit about what sensors give us.
So sensors, like you say, Paul, it gets pretty interesting, right? These are your inputs. This is your window to the world, right? Paul, you mentioned temperature, pressure. You can do pulse rate, right? There's a lot of bio sensor types. There's just about anything. If you can imagine an input type, there's a sensor that will give you that. Let's see, we're talking about, nearly unlimited selection, right? That's really the case. And there's lots of places where you can go to find sensors. And I have one website open now on my desktop, a place called SparkFun, right? This is a pretty popular place. If you do a search on the web and you say robotics, hobby robotics, or hobby sensors, or hobby microcontroller boards, or any of those searches, you'll find a lot of different things. So SparkFun is a good one. I also have this Adafruit Industries. This is good. They provide a lot of support as well. Lots of different things here with sensors and controller boards and motors and different things. And then I also have, and I don't know how to pronounce any of these places, right? Poalo. Robotics. And these guys provide a lot of support for their stuff too. They're all good, and these are just examples, right? We're not promoting the go to these and don't go to other places. These are just places that that we used as we went through this. But I have the sensors open here on the SparkFun site, and we're using SparkFun because I can say it,
yes,
Paul.
That's right.
It's important for our video.
That's right.
But if I scroll down a little bit, we can see that I've selected sensors, and so a lot of these were on the slide, right? But it's a little more detail here. Accelerometers, biometrics, capacitive current, flex, force, gyros. I mean, just all different kinds of things. If I switch to biometrics, we'll see, muscle sensors and pulse sensors and fingerprint scanners. I mean, really, when we say if you can think of the type of input that you want to get, there's probably a sensor that will help you. It's really true. So I think we get the idea there of
I've got one here that I just wanted
sensors.
to show. If maybe we can switch to that camera. So this is just to give you a sense of the size of these things. So this is a rangefinder, correct? Rangefinder. Yep. You can see how small it is. It'll either plug right into your board, or you can attach it to plexiglass like we've done with our robot, and then you can use it to sense range, which I will actually do a demo in a moment. Let me just put one up, a couple of others here.
And that one was a emitter and receiver pair, right? And the one that we're going to be demoing is a little bit different than that, but it's the same functionality, right? It's like little sound pulse that goes out and reflects back.
Yeah, and we'll show you how that works later. Here's another one. Maybe, I don't know if you're hardly going to be able to see this, but again, the point here is just the size. This is a current sensor, and it's really tiny. You can hide it on your board as long as your wiring makes sense and you can get at it. But the size is just extremely small, but highly functional. So a lot of the sensors are like that, right? You can put a bunch of these things onto your robot, and then they can do the work that you need them to do.
Yep. Some of the sensors, you'll take a direct measurement off of it, right? The rangefinders are generally pretty simple, right? You could either take a voltage or pulse width modulation. But some of the more advanced things, like the fingerprint reader, you're not going to get back a voltage reading, right? You're going to get back a more complicated message. So there's sensors that will connect for serial connection, or I to C, or USB, lots of different connection types, from just your very simple voltage, which makes sense for temperature and lots of different things, to the more advanced communication through serial or USB or I to C. So lots of options there too.
Now this sounds a little bit complicated, and it does get a little bit complicated, but you'll be surprised at how these robot board manufacturers have made it simple to use. So even though it sounds a little technical, I think if you have some technical acuity and you know how to program, you can put these things together, right? So it takes a little bit of practice, and you'll have to maybe tear it apart and put it back together, but it's not terribly complicated. So even though there's a lot of options, the board manufacturers and the sensor manufacturers have made it easy to do. So we want to encourage you to go out and try some of these things and do it on your
Lots of fun stuff to play with.
That's for sure.
Yep.
All right, let's move to motor types. So we've been talking about sensors, we talked about shields, and obviously if you want your robot to do any kind of motion, either move around, or like we're working on now, we're working on a robot arm. If you want it to have that kind of functionality, then you're going to need motors to do that work. So let's talk a little bit about what these motors are all about.
Yeah, and so we've been dealing with servo motors so far. And we did the continuous rotation servo, and then we switched over to the positional servo, right? A plus and minus 90 degrees, 180 degree range of motion. And that's great. And you can get a pretty powerful servo motor. But if you're going to move to a bigger, stronger motor, then you're talking these bigger DC motors and gear motors, things like you can power a wheelchair and, some big motors, right? And you can run those with some shields. You get a really high current, high voltage shield, and you can attach it to these tiny little microcontroller boards, and you can create these larger robots. You can, throw in some. We're going to be talking a little bit later about different wireless communication types that we can use, and so you can throw on an RF transmitter receiver onto this robot, and you can have this big giant motor on there, and you can have this thing sending back video of where it's at, and you can control it remotely from like a mile away, right? I mean, there's big hulking motors that you can attach to these things, so that's pretty cool. But the motors that we're going to talk about, like I said, we've already done servos. we're going to talk just briefly about stepper motors, right, and what those do. And we're going to do the DC gear motors, which is what we're going to use, and we're going to demonstrate. Stepper motors, call them stepper motors because they have a rotary encoder built into them, which allows them to very precisely detect the orientation of the motor relative to its fixed location to your robot. So a lot of them are 200 step increments, so 360 degrees divided by 200 steps, and they will track the rotations past multiple rotations. So it'll keep track of a lot. If it rotates 3 rotations plus 40/200ths of a rotation, right? And it can be very repeatable. So that's
what I'm holding
cool.
here. This is a stepper motor, right, Chris?
Yeah, and we don't use a stepper motor in any of these, but we just have one to show.
That's right.
But we could have used a small stepper motor for some of the things that we're doing. Positioning the sensor, the rangefinder sensors, right? We could have used it, and it's nice. It's very repeatable, and you can get that's a pretty big, strong stepper motor. You can get, Paul, for the 3D printers.
That's what I was just going to say, the 3D printer
3D
that I saw in your office, you have a couple of those on the 3D printers that uses the same.
So it's a good motor to use for the application that you need. Very precise, right? Like 3D printing, you want to be able to move very precisely, very incrementally, and very repeatable, reliable, right?
Yep.
So stepper motor is good for that. But we are going to be doing the DC gear motors, and that's what we're going to demo next. Now, a gear motor, DC motor, right, could be running at, let's say it's running at 10,000 RPMs or something like that. It could be less than that, but it's running at a particular voltage. The voltage will establish the speed. The current that it's drawing is based on the load, right? So they'll be rated as a no load RPM versus full load RPM and where it stalls, right? And then the current goes up as you put that load on it. So the current is something that you have to worry about with the microcontrollers, and that's where our shields come in, right?
Right.
And so we have a demo coming up that's going to show how we program the servo motor, and our first demo uses the pulse width modulation signals on the board to control the motor. In our robot, in our MS Guard bot, we have 4 gear motors in that, and we're using a different shield, and that shield is programmed differently, and we kind of wanted to show both, and we're going to make all the code available for the demos and for the robots. So hopefully it'll all be set up for you off the MVA site. So that you'll be able to find this code very easily, but you'll have Paul and my email addresses. If for some reason we don't have it up and readily available, you can shoot us an email.
Yeah, we'll make sure
we get it set up. So 2 different ways of controlling the same type of gear motor. Both of them, they operate the same way. It's going to be the higher the voltage, the higher the RPMs, but the loading, the programming is a little bit different, and we'll see that when we get into it. And I think we'll probably touch on as we get into the later modules, we'll touch on the coding for the other gear motors as well.
Yep, but before we get to motors and doing the demo on motors, we're going to look at sensors first. So we've been talking about sensors a little bit, but we want to show you one of the sensors that we're using in our robot, which is the rangefinder, the ultrasonic rangefinder. So, as we thought about putting this robotic arm together, we wanted it to move around, and we wanted to know how it would orient itself in a space, which you'll see later. And then it had to be able to detect whether or not something else was in the space that it was working in. So we needed to be able to detect range, essentially, and detect distance. So we had to figure out how we were going to do that, and we had a number of options. Chris settled on the ultrasonic rangefinder. Maybe you can talk a little bit, Chris, about why you did that and what considerations you underwent in order to make that decision.
Yeah, Paul. So we really had 2 choices, right? Because a laser rangefinder is an expensive kind of device, or can be expensive for us. So we had IR, infrared sensors, and we had ultrasonic. And we knew that we were going to be in a studio, which we weren't sure how the lighting was going to be, but infrared is sensitive to lighting. It's not going to be something you'd want to use out in the daylight. but ultrasonic is using sound waves, so it doesn't care about the light. And we knew we were going to be in our little fiberglass. We're going to be in a plexiglass enclosure, and the IR is going to go straight through that, so it wasn't going to see our walls. Our boundary was going to be transparent to the IR sensor, so it's going to be measuring something outside of the boundary, and we wanted to measure at the boundary. So it was pretty easy for us to land at ultrasonic. Ultrasonic sensors use sound, so it cones out, the signal cones out, so it's not going to be precise like an IR sensor. So those are the kinds of the balances, right?
Yeah, so that was one of the things we wanted to talk about, is that sensitivity. Obviously, when you get a reading back from the sensor, it doesn't tell you it's so many centimeters from a wall or from an object. What you see in code is actually what? It's a measurement of electricity. Is it amps?
Yeah, we get a voltage.
Or voltage, yeah.
Yeah. The sensors that we're using, we could have taken a pulse width modulation value, so it's a ratio kind of a thing, right? I mean, pulse width modulation. But there was also a voltage output, and that's what we're doing. It's pretty straightforward. The Arduino boards kind of add a layer of complexity to that, where they give you your voltage from your inputs, a ratio of your input voltage, for us 5 volts. And then they say, okay, we're going to give you 1023 increments in that full range. So if you supply it with the 5 volts, you're going to get a reading back which is between 0 and 1023. So 1023 for 5 volts. And then each volt off of the sensor is going to be proportional to the distance that you're measuring, right?
And so you have to do that
conversion. So there's a few different things that you have to think about. But we think about it as the sensor reading, the voltage reading, and then the distance reading.
Great.
Right. So 3 steps. But it's it sounds complex. Maybe it sounds pretty straightforward, and it really is pretty straightforward. So
let's go into our demo
and look at it.
Let's take a look at it.
Yeah. So I have Visual Studio open here, and so the first thing you can see is that we set up our variables as usual. I got a restart required, Paul. That's great. So we have the sensor pin, so it's taking our reading off of one of the analog pins. And then we have, like we say, an analog reading, the sensor voltage, and then the sensor distance, and the distance multiplier volts per inch. So we go in here, scroll down a little bit into setup. So we're saying that we're off analog pin 0. Mm-hmm. We just say, I just set it, initialize these values to 0. And then the voltage multiplier, volts per inch, that is provided by the sensor manufacturer. And then we set up our pin mode as input. Down in our loop, we take our analog reading off of so analog read, sensor pin, right? And then we're going to multiply, if we get to our voltage. Like I said, we have 123 counts for the full 5 volt range, and we multiply that by our analog reading. Right? So then we have an actual voltage between 0 and 5 volts. And then to get to our distance, we have our distance multiplier, volts per inch, and we're dividing that by sensor voltage. So if you looked at the units, then the units balance out to a distance.
That's
unit,
cool.
Right?
And that doesn't look like it's very difficult code, right?
No. The code is simple.
Once you get the values, then the code is really simple.
Yeah. And let's see. We are going to run this in the debug mode. Most of the time we've been running without debugging, right? But in this case, we want to know what our reading is, and our little demo setup here is not going to, it doesn't have a display, so it's not displaying the distance. So we want to see what the distance is to see how accurate we are. And we'll talk a lot about that in the upcoming module. But let me go ahead and...
Actually, before you run it, let's take a look at the little kit setup we have here, if we can switch over to that. So all we've got here is you can see the sensor here. This is the ultrasonic sensor. We've just got a white piece of paper, and it's along a ruler, so we can tell how accurate our setup is. And let me see, make sure I don't get this too far off here. So we'll just stick it right there, and now we'll see if it's actually going to work. But you can tell we're just going to bounce the ultrasonic signal off of the white piece of paper, and then we'll get a reading, and that's what you're going to see in code. So if we can go back to the code,
All right.
we'll look at that.
So here we go, and like I say, we're going to run this by starting our debugging. We're going to get a little debug screen thanks to Visual Micro.
That's right.
Right, which is the add-in to Visual Studio.
Earlier modules, yes.
And okay, Paul, here we are, right? We can see over in this area. See if I'm not sure if I make that bigger, if it's gonna, what that's gonna do for us. No, it just makes my code window bigger. So you might be able to see that it's saying that we have a distance of 9.5, and it's flipping back and forth between 9.0 and 9.5. So that's in the appropriate range. Like I said, in the next module, we're going to talk a little bit more about calibrating the sensors. Mm-hmm. But we've seen in this demo, we've seen how do you actually take a reading. And like you said, Paul, it's pretty simple, right? It's an analog. We're just taking a reading off an analog pin and then applying the appropriate conversion multipliers to get it from this 0 to 1023 to a voltage, and then from a voltage to a distance.
Now, we didn't practice this, but could I stick my hand in the middle of that sensor and have it change?
Yeah, it's still reading. We can kind of see that it's getting some readings. So now, if we switch back, now you can see it's flickering. So this brings up a great point. For these sensors, they're going to report a distance of 6 inches for values less than 6 inches.
I see.
So it will detect that something's there that is less than 6 inches away, but it will tell you that it's 6 inches away. So always you need to understand what your sensor is going to return. It's an important thing.
And that's true for all sensors, right?
You should understand what
understand
understand
the data that they're returning. Yes.
Yeah. And these particular ones, 6 inches, it's because of the sound pulse and the reflection back. When you get something really small, it's not going to be accurate, so they return a value of 6. Right. And it actually goes out to 25 feet, so it's a sensor that's not intended to be used for really close distances anyway.
Yeah,
right?
that's great.
25-foot full range.
Cool. So that's the sensor. That's the sensor piece of it. Now we're going to switch over to the motor piece of it. This is what we had introduced earlier, and now we're going to talk a little bit about controlling gear motor speed and how we control direction using these DC motors. So the first thing we want to look at is speed and direction. So how do you control speed and direction using code against these both the shields and the Arduino boards? So let's talk a little bit about that.
Yeah. So for the DC motor, the current flow establishes direction, right? The higher the voltage, the faster it goes. We talked about that before. But we didn't talk about reversing, right? So you reverse the polarity of your voltage source, and it will go in the other direction, right? And that's so that's pretty straightforward. Like we said, you put a bigger load on the motor, the current starts going up, so it can be important to have a sensor that reads current. And we're going to swap out these little setups so that we can run this next one. And I am going to just plug that in here in a second.
And what about direction? How does direction work for these DC motors?
Right. So that's the old flippy floppy on.
I'm not concentrating, so you probably just mentioned that.
Yeah. No worries. So speed, direction, current flow.
And then, the other thing we had in our slide is the how the shields work. So how does the shield and the libraries work together? Because obviously, if you want to control a bigger motor, this is where the shield can really be handy. We talked about this earlier because it can allow you to drive bigger motors based on the shield.
So very good. So this particular one that we're going to be demoing, as I said, this shield is a little bit different. It would allow us to run up to 2 motors and not as high amperage as the one in our robot, but it will run 2 DC motors, and this is using the pulse width modulation lines to control direction for us. and speed.
That's awesome.
So we use, and we'll see in the code here, we can probably have Barry flip back and forth for us. So we can see the pin for motor speed, pulse width modulation A. And like I said, this will do 2 different motors. Yeah, and I can't talk. So one for direction and one for the speed. And we're using pin 3 and pin 12. And we don't have a second motor set up, so they're both motor A. Then then it's using forward and backward. So we're setting a value of high for forward, and these are internal variables.
Yep.
And then we're setting our speed, stop speed at 0 volts, and our max speed at 255. And that's our full range for this. That 255 is not 255 volts, but that is the stepped increments. That's our incremental value. So we can specify anything between 0 and 255, and those are increments, right, of how fast it'll go. In setup, we just attach, we set up our pin modes as outputs because we're going to be controlling the motor, so it's not an input, it's an output. And then we set our direction to forward and our speed to stop. And then in our loop, we have this motor test speed function that we call. And let's look at that real quick. So we're going to set it up. The first thing we're going to do is we're going to say forward at a speed of max speed over 2, so half of full speed. And we're going to leave it going at that speed for a little while, and then we're going to go to full speed. And then back down to half speed, and then to stop. And then we go backwards, right? So it's really pretty simple.
Yeah.
So most of the work was up above where we were setting up our pins,
right,
and our ranges. So we will go ahead and run this, and we know it will work. I am going to say build. And a little screen down here will say whether or not that worked, and I had it closed, so it's not saying it, so we'll just assume that it's going to work. And let's start it up. And did we plug it in? Oh, we did. All right, so there it's going. So it's going half speed, and then full speed, and down to half speed, and then stop, and stop for a little while, and then it should go the other direction. And this looks pretty simple. And it is pretty simple, right? It is pretty simple to do this. The other board that we're using, the other shield that we use, is just as simple. It provides a library. You mentioned libraries before. They provide a library and some nice documentation on how the functions within that library. The benefit to the other shield is that you can have, it's using I to C with the library, so it's not taking up any of the pins. This board is using some of our pulse width modulation pins. For our robot, the MS Guard bot, we're using 5 different servo motors. We're using the 3 sensors, so we have we're using a lot of the pins. So it's nice to have all those pins available to us with the shield that we're using.
That's pretty cool.
And those shields are stackable. The I to Cs are addressed. Right, so you can change the address of the shield if you had a conflict, because you're using a large number of shields. So if you had a conflict, you can change the address, and that pretty well covers it, I think, Paul.
Yeah, but now you can start to see if you watch the previous module 4. You can see that all these pieces start to come together, and you can get a sense of how you can actually do some real work. So, for example, if you pair a sensor with a motor like this, you can have a door open, or you can have an arm do some work for you. But you take all these individual pieces, you put them together, and you can actually do something functional, which we're going to show you in future modules, how we bring it all together in a single robot. So yeah, these pieces are definitely critical, and it's nice to isolate the individual parts so that we can show you how the parts work together in a future.
Yeah, I think like you say, our big takeaway here is there's all kinds of sensors for inputs. There's different types of motors for outputs. We didn't really talk about a linear linear actuators,
Yep.
right? We talked about rotary motors and the servo motors, angular positioning servos. But there's linear actuators that you can use. You said lock a door, right? So you might want to just move in a linear motion, right? So there's actuators for that. There's just all kinds of stuff, all the different sensors that you can imagine as your inputs, and then you use that input to help you decide what you want your robot to do. It can be a lot of fun.
It is. And now in Module 6, what we're going to do is show you how to take this rangefinder, this sensor that we showed you earlier, and actually start to map an area and do detection of objects when an object intrude into that area, and how you know that there's something else there. So we're going to show you how to bring this together now to actually create some cool mapping, and then we do that in the context of a robot that's going to be able to move around in that area. So that's Module 6.
Yep, and we talk about some calibration too. Right?
That's
I mean, I don't want to jump ahead, but
yeah, we'll do
that's a big part,
calibration in Module 6 as well. So we'll see you on the other side of the break. All right, welcome back to Programming Robotic Systems with Visual Studio. We're continuing to work on our MS GuardBot, and we're going to look at now how the GuardBot will map areas and do object detection. So this is where we get into the specifics of using the sensors to map an area and then figure out if there's an intruder in that area. And later on in our demo, you'll see the GuardBot, MS GuardBot, going after the MS BumpBot and trying to disable him. But we'll show you that later on. So very quickly, what we're going to do in this module is we're going to again look at the functional requirements for mapping an area. Talk about positioning, calibrating sensors. We'll give you a demo of that. Then we need to calibrate wheel movements. We'll go back over to the pit and show you a little bit about how we calibrate wheel movements so that you can see the importance of doing that, using the robot. And then we'll bring all this stuff together. The GuardBot will come alive, go after the MS BumpBot, and we'll see if he can track him down and disable him. Okay, so that's what the module will look like. Now I'm going to turn it over to Chris. Chris is going to get into some of the details now on the functional requirements for mapping an area. And there's some very specific technical things you got to keep in mind as you're programming these sensors.
Okay, very good. Thank you, Paul. All right, so first thing, if you're going to map out an area, you need to understand, you have to have a point of reference. So you have to understand your reference system. That can be an external reference system. Global Positioning System provides an external reference system. You could use that to map out an area. Or you can have a more local reference system, or you could have north, south, east, west, right? A compass can provide some external as well. For us, we're going to be in an enclosed area. And so we are going to use a feature of that area to use as a reference. That's going to be, for us, it will be a wall. Paul, once we have, could we switch back to the slide real quick? Perfect. Movement and tracking orientation. So these are the things you need to think about, right? External, internal reference system, movement and tracking orientation, and then coordinates, boundaries, and object mapping, all right? So, and you have to do it in that order. So when we get to moving and tracking orientation, that means you're going to move around in the area that you're mapping. Sometimes you can't map the entire area if you're stationary, right? There could be objects that obstruct your view, or the contours of the area could be such that you can't do that. So, so you want to be able to move around, but as you move around, you have to keep track of your reference points, right? If there's a cluster of trees off in this one position, you want to keep that. As you turn and move, you need to keep reference on that. Okay, so I think that's pretty clear. And then the last thing is object detection and mapping. All right, so you're going to, as you establish your boundaries of your area, and then you work within that, you locate objects, you keep track of them on your map. Then, once you've finished your map, you can detect new or moving objects by comparing what you see with your map. And we do all these things, Paul, all the time, right? We have so many different senses. We have our sense of sight, hearing, smell, even our ability to feel temperature changes or the wind. All these things help us. And so we take it for granted. We got to supply all that information to the robot, and that can be a lot of work. So it's harder for the robot than we might think.
Now you had talked. We talked a little bit about this offline, and we talked a little bit about it earlier in the presentation. But we're using very specific types of sensors. What other sensors are there out there? I don't know if we get to that later or whatever. But can we talk a little bit about the sensors that we do use?
Yeah. All right. So we're using ultrasonic sensors, right? We talked about that a little bit earlier.
That's right. Okay, that's right.
We did, and but basically we compared infrared and ultrasonic. We're using ultrasonic for this, in part because we have plexiglass. Infrared would penetrate through the plexiglass. Ultrasonic bounces back off. And it's less sensitive to light than infrared. So we're using the ultrasonic sensors. We have 3 of them mounted here. I think let's just make sure we stay on track with the slides.
Yeah.
Let's see where we are.
Great.
Yeah, I think we can move on past here. Methods for calibration. No, we're good. Let's stay here. I'm sorry. Sensor mounting and positioning. Right. Okay. Well. You need to think about what your robot's going to be doing and where it's going to be working, and its physical geometry, right? So as you're positioning it, you might say, okay, I would like to use a fixed positioning system to dampen out some vibrations, or I want to position on an arm so that I can use fewer sensors. That's what we're doing. You need to maintain line of sight, but you can't have some big giant arm if you're going to work in a small space. So we elevated, we wanted to make sure that we got fewer false positives off the ground surface, right? So if we send out a pulse, an ultrasonic, of course, we talked about this, it sends it out in a cone, it's a sound wave. If it bounced off the floor, if it was too low and bounced off the floor, we'd get a false low negative, a false small signal. And then let's switch back to the slide again. Why calibrate? Okay, well, sensors are going to include some error. There's different types of errors that they can include. You can have an offset error where the 0 position on the sensor, it should be reading 0. It's reading some value, either positive or negative. It can be nonlinear across its range. It can have sensitivity error, so it could be reading, let's say, we talked about this a little bit, that you're reading a voltage, you have a multiplier to convert that voltage into a distance. The multiplier that's specified for the device is off by a small amount, 10%. And so you need to adjust for that. That's a sensitivity error. And then you have noise, Paul, and that's the bad one, right? Because that's random, you don't know what it's doing, you need to deal with that or get a different sensor.
Right, and then the last thing we have is to talk about methods for calibrating sensors and filters. Right. We're going to show you some of those methods, but are there other things that we should consider here? So
we touch on it just a little bit, right? There's some different things, right? For an offset, you can calibrate. Some of the things you can detect as part of your calibration, you can compensate for. Other things like noise, you can't. You have to deal with it. And we're going to do that. We're going to filter out some of the data. There's different algorithms that you could apply. We're going to stick very simple, but we will show you how to do that because it turns out one of our sensors was not up to snuff, and we will deal with that. So let's see what we got.
Let's go right into the demo. I think that's our next step here.
Ooh, all right.
So we can jump over the code.
We are set up for that. I'm going to adjust the size here. All right. Just really quickly, we're in the code for the GuardBot. There's a lot of code here. But we are going to, you can see some of the Booleans here, right? We're going to move down into setup. And we're going to say, okay, well, we have distance between sensors. But the things that are important for us, we're setting all of our values here, right? We get down in here. And we are going to say that we're going to perform diagnostics checks. That's true. We're going to perform these sensor diagnostics. That's true. Okay, so very good. Let us go down into the loop, and let's read this. Okay, if it's true, we do this. So Visual Studio allows us to go to the definition. We can then see what we're doing in here. All right, fine. We're taking these readings off these sensors. Well, first we're positioning them, then we're taking readings. Let's go ahead and, again, whoops, wrong thing. Let's again go to the definition.
So like the other programs that we looked at, you have the loop that's constantly running,
Yep.
and within those loops you're calling subroutines, and those subroutines are doing work and returning data.
Right.
And so it's essentially a more complex version of that same basic structure. That's what Chris is.
That is correct, and we're just kind of drilling down into our diagnostics as we go. So we can see, all right, we know we're doing diagnostics, so we want to see a multiple readings. We know that we have a bad sensor. We found out with the diagnostics. The iterations here set at 50 as a result of some of the work that we've done. So let's go ahead and run this. We've set up some breakpoints, and we're using Visual Micro's debugger to take a look at the data. So we'll start it up. What we're going to do, we're going to see it. We'll see the sensors initialized. We'll just switch over to that camera view. Yeah, that's good.
You need to turn this puppy on.
Yeah, go ahead and power those up. All right, and we'll see those start moving. It's taking some readings, and we'll let that go. You'll see that, get the idea of that. Now let's switch back over to Visual Studio. And we can see over here on the right side, we see the debugger information. Let's focus on this top area, because that's the individual readings as we loop through the 50 readings. So we're going to watch, see if we can. It's changing pretty fast, and it's also changing position. So it moved up, but we see that we had a value of 52. You can see a lot of variation there, Paul. Mm-hmm. Right? See a lot of variation, and then down below we've filtered that information, and we have what we're calling an average distance smoothed. Right?
And you're only reading final positions of those sensors. You're not reading all the data in between as it's scanning.
Yeah, we're waiting for it to stop.
Right.
After it stops, then we take readings. And it's just taking readings in the room here.
And how many times is it reading per second?
This particular sensor allows you to take readings every 30 milliseconds. And so we have 3 sensors, but we're firing all 3 of them every 30 milliseconds.
And that's why there's so much variation within that time period that you're reading, and so you're just getting the average of those various readings. Yeah,
it turns out that a couple of these sensors are working pretty well, and just one of them is working more poorly, and it's got some noise in it. But we're processing all 3, because we have to process the one, we might as well process all 3. All right, so I'm going to talk just briefly about what we saw and what we did, right?
Yeah.
So we were seeing small readings, rather than seeing a true reading. We were seeing readings that were smaller than we would expect. So we looked at the standard deviation, we looked at the averages, and we looked at the individual readings. We saw a large percentage of small readings. So we said, okay, without doing a detailed analysis to figure out, oh, this is a chi-square distribution of, typical electronics, this and that, we're like, okay, I think this is noise. I think we're getting some kind of low signal off this one sensor. So let's average, let's sort the data, capture the data, sort it, and then take the top 25%. That'd filter out the lower readings, and we'll see what we get, and we'll see if we're getting now at our calibrated distances, whether we're getting good enough readings. Turns out we did. We stopped our analysis, moved forward, and we're able to get the sensors now to give us pretty good readings within about a half an inch in our area where we run these demos. So
the sensors aren't giving you a distance. They're not saying like you're 5 inches from the wall or 3 feet from the wall. They're giving you what, a voltage?
So yep.
Kind of
so we do get a voltage. These particular sensors can provide an analog voltage. They can provide a pulse width modulation signal, or we can get a serial connection. We're taking a nice analog voltage off these because that's nice and easy to work with, but it is a voltage. The Arduino is going to, when we read an analog pin, it then scales that between 0 and 1023, I believe. So now we're getting an integer representing 0 to 5 volts. The sensor then says, hey, for every volt, that means X number of inches or meters. So then we'd have to convert first from Arduino's integer scaled across 5 volts, 5 volt reading between 0 and 1023. So we scale that first to get to 0 to 5 volts, and then we scale the voltage to be a distance.
Right, and so you knew it was off because you knew you had a known distance of a certain amount of centimeters or inches, and it wasn't reading that distance properly when you got the voltage back. So then you just make your calculations based on that error.
Correct. We set up the sensors at 12 inches, 24 inches, and I think 48 inches, took readings off those. It's not full scale. These sensors go out to 25 feet. We probably should have calibrated across the full scale, but we knew that we were going to be using it in a small enclosed space, so we only calibrated at those distances. Came up with our appropriate value for scaling for sensitivity to accommodate both the Arduino analog input and the sensor. And we applied that factor. We are still seeing the errors, so then we filtered off that, ended up with our final value where we're accurate to most of the time within about a half an inch.
All right, so now we have the code handling the sensor errors, so we know that the sensors are going to be fairly accurate. The next thing we want to move into is talking about wheel calibration, because now that we have the sensors working, we need to make sure that the wheels are calibrated properly so that we can, as the robot moves, it will be moving in a predictable way. And so now we're going to talk a little bit about wheel calibration.
Yep. Okay, so we can see, so one of the things we have to recognize is taking these sensor readings, because we need to filter, taking these sensor readings takes time, right? It's taken it almost a second to take 50 readings, spaced at 40 milliseconds, 50 readings about a second, maybe 2 seconds. Boy, how's my math?
Yeah.
So it's taking some time. So if we're moving around in the area or mapping an area, we don't want to move a little bit, take a reading, see where we are, because we need to maintain our reference. So we can't just move all big, long distances and then hope to find our reference point. You have to move incrementally. But doing that takes so much time. So what we want to be able to do is move a calibrated distance using our motors to move a known amount. Then we don't have to make so many small moves and recheck our sensors. So that's what we're doing. That's one of the things that makes it so important. So what we're saying here provides awareness and control. Okay, you keep an awareness of where you are and where you've traveled to, so that you know where your reference is, and it enables faster movements. Okay, so that's linear, forward, backwards. Same kind of thing applies for angular, but it's even more important. If you, in an extreme case, you put the robot in a circular enclosure with white walls, and you set it up at a particular orientation, and you tell it, okay, now you need to do turn 360 degrees. It has no way of knowing, it has no reference point that it can measure. It's in a circular enclosure. Once it gets to the center or wherever, it's going to be trying to do these things. It's going to have a very hard time. So being able to move a calibrated amount becomes even more important in those cases. And that's an extreme, but it applies across the board. So that's angular and linear. That's why we want to calibrate the wheels. We are going to do that as a demo. We're going to do it in Studio B so that we can move bigger distance. We don't want this guy going off the table.
Yeah, so let's go over to the pit, and we'll do our wheel calibration there.
All right, here we are, back over here in the pit. We have the MS Guard bot here, and we are going to run the wheel speed diagnostics test here. What we want to do is we want to make sure that we have controlled and understood movements that are repeatable, both linear and rotationally. So I'm going to start this up. We're going to check out what it does. All right, it's just doing its initialization. It's going to start moving here in a second. We'll ramp up the speed, ramp back down. It's going to go forward, reverse. Should move back to the same position that it was in before. All right, did that. Very nice, right back to the line. Now it's going to try a rotational 90-degree turn. Okay, went a little bit far. We can adjust that in our code. Now it should spin back the other way. Should be a fairly repeatable move of 90 degrees. Looks like it moved back 90, it moved forward too much. So we have a clockwise, good, counterclockwise, a little bit off. It's going to loop through that now. It's going through that same thing. But you get the idea. That finishes up this demo, and I am going to head back over to Studio A.
Okay, you saw in Studio B in the pit how we used the robot to actually help us with the calibration, the wheel calibration. You saw how that was done. Now we're going to try to put it a little bit more together by looking at the how we use the sensors and the wheels to do coordinates and object detection. So we're going to bring these two pieces together and talk a little bit about how the sensors help us navigate the robot within that space. And Chris is going to talk a little bit about some of the aspects of this.
Okay, very good. So first off, we need our reference point, right? So we put our robot into this area and say, okay, you need to perform these tasks. You need to map out the area. How is it going to map out the area? It needs a reference point. So recognizable object that it can maintain its position relative to. The next thing you do is you're going to choose a coordinate system. And there's basically two coordinate systems that you have to choose from. Well, there's a lot more than that, Paul. But for us, we're talking 2D, right? Two-dimensional. And so we have a Cartesian coordinate system, which is our standard parallel grid kind of a thing, right? And then we could choose a radial polar coordinate system, which has a center point and with angular positions at a radial distance away from that. And that can be good if you're, say you have some type of home base that you're interested in maintaining or returning to, and you want to map out the area relative to that home base. You have a robot that can work in a geographically challenging area, but it needs to charge its battery, so it needs to return to that point. So it slowly makes its way out to these different, more remote areas. It's going to map things on this at an angular position. There's this big tree, there's this big boulder at 30 degrees at 400 feet or whatever it's doing. So there's reasons for that, but we're sticking to a Cartesian coordinate system. So what we're going to need to do is then align to the axes, right? So we come in, we find our reference, which for us is going to be a wall. Then we will align to that wall. So now we know if we move linearly, we're maintaining that reference, which is that important thing that we talked about, right? Maintain your awareness of your reference system. We're moving along the axes. Now if we can move 90 degrees, we can move along the other axes. So that'll be important to us. Then once you've established your axes, your coordinate system, you're able to move along one of those axes, then you start mapping out your area. We'll start looking for things within that area. Either we move to them or we can move our sensors to find these objects that are closer to us than our boundary distance. Create a map of that. Once you have your map defined, and if you do detect an object within your boundaries, it's good to move to another area on your axis, a check your reference, know where you are, locate that object again, because you will have errors in your sensors, so you want to kind of triangulate on it to verify that it is where you think it is. Because you don't want to run into it later or think that it moved or something like that, so you want to have a good map to start with. Once you have your map, then you're able to detect something new by comparing what you know, your map, to what you're seeing in the current time. And that's pretty much it.
So a lot of this sounds like it's way beyond beginner. Like a lot of what you just described sounds pretty complicated. Is there anything we can provide that will help people get going, particularly for users that want to just get a robot moving into space?
Yeah.
Is there anything that you can recommend to?
So our example is really a pretty simple one, right? We have a 4-foot by 4-foot area with no objects in it at all. So we have a very clean space. We align to one wall. We then rotate 90 degrees. We align to the next wall. Now we've established these two axes. We're rotating our sensors through 90-degree turns. We find the distance to each of the 4 walls, and then we say, okay, we know our coordinate system, we know where our boundaries are. Let's move to the center and start looking for something new to show up. It's pretty simple. I mean, maybe it sounds a little bit more complicated, but get a piece of graph paper, just graph it out, think what it is. This example is not hard. You get to an irregular boundary shape with objects that are within your boundaries that you need to map, it can get pretty hairy, especially maintaining your reference point. But if you do these things, I think it's not so bad as it sounds.
Yeah, and if we post the code, you'll get to see kind of how we put it together, and hopefully it'll make sense. It is very logical in the way that Chris set this up, so just looking at the code will probably help you understand a little bit better what Chris is talking about here. We're using some kind of technical terms, but at the end of the day, it's just getting a position and then moving the robot within that position as the position changes. So hopefully it will make sense. We're going to go back now to the pit, and we're going to bring all of this together. The wheel movements, the sensors, and the arm, all the things that we've talked about in the past couple modules. And we're going to put the guard bot, MS guard bot, in the pit, and then we're going to introduce the MS bump bot, and we're going to see if the MS guard bot can find him and shut him down. So let's go back to Studio B, back to the pit, and
it'll be fun.
And bring this together.
Here we are, back at the pit. We have the MS guard bot here with us, and we are finishing up with its I Am Alive demo. So he's going to do his thing. He's going to start looking. We're going to introduce the modified MS bug bot, and the MS guard bot is going to turn him off for us. All right, we'll see what happens. Small children might need to leave the room. Okay, so he's initializing now. The next thing he'll do is he'll look at the walls. He'll say, hey, I need to align to one of them because he's oriented himself in the space, right? So he's got to pick an axis. Let me start that again. I see that he's having a sensor overload. Make it a little bit easier for him. All right. Should see this wall, should say, hey, I need to rotate a little bit. I will adjust. Okay, it's going good now. And he'll just keep moving a little bit at a time until he feels like he's aligned to this wall. That's the first part of establishing your reference point and aligning to your axes. Okay, he says, I'm aligned. I'm going to start looking around. I'm going to move along the axes towards the center of the area, because that's where he wants to be. That's where we told him he needs to go. It's the best vantage point of a guard to be looking around in the space. He says, okay, I'm aligned that way. I need to rotate 90 degrees. As we saw before, he got a little too far. Hopefully he's going to rotate back. Looks like he's working his way. And we would adjust that 90-degree rotation on our code so that it's a little bit closer, because it's a bit too far, really. But that's easily fixed. Now he will keep the slow rotation till he's aligned to this other wall. So he's maintaining. He understands this is his reference wall. This is wall number 2 that he's picking up. And he's now getting that alignment, move towards the center. And he's got just a little bit further to go. Once he's moved to the center, he will start scanning the area for intruders. All right, a little bit more. I'm coming over here to our modified MS bug box. So now you can see he's moving the scanners around. He's scanning the area, taking discrete readings at about 30-degree increments that we programmed in. All right. Now, he knows what the distance is for the perimeter wall. If he sees something that's significantly closer than that perimeter wall, he's going to move after it. Oh, setting this guy loose. Whoops. Hey, don't climb that wall. He's upset from earlier. Shut him off just for a second. Put him back together. All right. Try and do a little bit better job of this. Put him back in. Start him up. And let's see what happens. All right. Bug butt should start up here in a second. And he's got to be about, I think, maybe 10 or so inches away before this guy's going to see him. He's going to move off that wall. Now what we've done with the MS BugBot here is we've added a kind of a modified switch up on top. So we have a, oh, I thought he was going to head right for him. We have a handmade switch, right? So we have one of the wires is connected to ground, the other is connected to a digital pin, so that when the arm of the GuardBot swings over the top, hopefully over the top, of the BugBot, he's going to hit this wire up here, and it's going to come into contact with the other wire, which is connected to ground, and he'll get a ground signal, and this guy will say, I got to stop now. And here in a minute, I'm gonna give him a little help of moving closer, and we'll see what happens. Oh, come on. All right, that's gonna get kind of close. Seems like that should have done it. Will he react or no? Oh, all right. Whoop, he did. He was just slow to move. That was terrible. All right, well, that was it. That's what we got. No carnage today. All right. We are now, that is our final demo for Module 6. And we are going to, or I am going to go back over. We're going to finish up with our final review of Module 6. And that will be it.
All right, welcome back to Programming Robotic Systems with Visual Studio. My name is Paul Party. I'm here with Chris Howd.
Hello.
If you missed previous modules, you'll definitely want to go back to the one we just recorded. We got to see the robotic arm chase down the little spider bot and or the little what do we call that first robot there?
A little bug bot.
Bug bot. That's what it was. And we're not going to spoil what happened there, but if you missed it, you want to go back and watch. Yeah. But what we're going to do now is talk a little bit about wireless control and integrating wireless control and communication into your robot. This is a really cool space because this is where you can start to control your robot without having it automated. So it's essentially now the human becomes the
it's a lot more fun, right? You're interacting more.
That's right. Yeah. And so it's really cool technology, and there's a lot of options. We're going to walk you through some options, and also, Chris and I think of this as kind of the seed for what's becoming known as IoT or Internet of Things. So, for example, I have a Nest thermostat in my house, and it has a little radio controller that talks to my router, my home network, and that's how Nest communicates with the internet and can update software and all kinds of things. So when we start to have devices that have these controller boards on them and then this wireless communication, then you can do all sorts of things. Yeah. The devices can talk to each other.
Yeah, and it wouldn't have to be wireless, right? I mean, it could be a direct wired connection, right? But wireless makes it a lot easier, right? You don't have to be, like your home doesn't have to be wired.
That's right.
You can, when you're using wireless or Wi-Fi or whatever.
So this is kind of the seed of that. This technology is the seed of what we're going to see as the Internet of Things technologies really starts to blow out. So let's talk a little bit about what we're going to do in this module. So we want to introduce you to what wireless control is. We'll talk about some options, radio frequency, Bluetooth are a couple of options. There's others that we'll just briefly cover. And then we're going to look at a very specific type of technology called XP, which is radio frequency wireless control. We'll do a little bit of a demo. And then we're going to show you the MS SpiderBot, which is where we integrated the wireless control into the robot, and then we're going to be able to control it using a PC. And we'll go back to the studio for that and show you how that works. So this is really about just breaking down the wireless control options and then showing you how we integrate those options into a working robot. All right. So let's talk about what wireless control is. We'll do a little bit of an introduction just to introduce you to the main ideas here, and then we'll show you some cool stuff. Okay. So Chris, you want to talk about some of the pros and cons of wireless control and what's involved? What you have to consider?
So I guess to start out, right, like we said, you can be controlling this thing from somewhere else. You are controlling it, right? So you're not doing all the programming and then setting it loose like we did before with the other robots. Now you're actually getting to interact and do your thing, make it go this way, that way. So the device can move more freely, right? the MS SpiderBot could move around this room. It doesn't have any wire. It's not tethered, right?
That's right.
And then, it's the fun part of we get to make the decisions for it. Cons, it costs more money, right? If we didn't have wireless control, that's something less you're spending money on. The wireless could be slower. Your wireless connection could be slower than a wired connection. In this case, we're doing a little robot that wanders around, so it's the speed is, we're not communicating a lot of information,
That's
right? So speed doesn't matter. Still have the cost. Not super expensive to get the receiver, transmitter receiver pairs, to get the pair. I don't know, maybe $50 would be average. When you get to the extended range, so RF, you can either have a kind of a shorter range, lower power, or you can have the long range, higher power. With the long range, maybe you're talking a little bit more money, but the power consumption is just as big a deal, right? Because you'll use a lot more battery power. So if you have a remote device a mile away, you need a good power source, and if it's a wandering little robot, then you need to think about the weight of the battery pack, right?
Yes.
So that would be a con. Then you need the user to be in control in some cases, right? It can have some autonomous as well as user-controlled activities. When it's about to run into a tree, it could stop. Some kind of thing like that, right? But you would need to then maneuver it, right? So you can have the mix of autonomous and user-controlled, but a lot of times you would then need the user to control it, and it couldn't do its own thing.
Right, and we've talked about using many devices. So you can use a small little slate. You can use a phone, particularly if you're using Bluetooth. You can use a phone to control your robot. We're going to use a laptop. But then the cool thing about these different technologies is based on the technology that you choose, you can control it using different devices.
Right.
So we'll show a little bit of how that works as well.
Yeah. Right, and that's the next thing right here on this intro slide. We're talking about, you can use radio frequency control like what we're doing, but there's Bluetooth, which is, pretty standard in most devices, so it's on your phone probably. So that can be fun, you could just control your robot from your phone. And then we have Wi-Fi, right? So you're connecting to your local network, and then you could control your robot from your website, which would be fun as well. Then we have things like NFC and GPS that we'll talk about a little bit as well.
Yes, great. So let's talk a little bit about radio frequency and some of the pros and cons of this, and then what's involved in using RF wireless communication in your robot.
Yeah, so RF, probably one of the big things is the range that you get from RF. So you can, like I said, maybe you get this higher powered module that will get you 2 miles. When you think of RF and range, you think of the remote controlled airplanes.
Yes.
And the drones, right? Is what the popular thing
That's
to call them now. So you have a good long range out of them. It's cost efficient. Like I said, you get a pair for $50, maybe a little bit less than that as well. And there's lots of options, right, as well. You do have to think about the trade-off between the range and the power consumption. In the case of our MS SpiderBot, we didn't need a lot of range. So if we used the Pro module, we had to add a battery. Didn't have to, but we did add a battery pack because the small battery that we were using for the controller board drained pretty quickly when it was also powering the RF transmitter. So you do have to think about power. And then communication speed for us, it wasn't a big deal, but if we were transmitting video over RF, then we would care about the speed. So those are some of the characteristics of RF.
And how does RF compare to Bluetooth? That's what we want to talk about next.
Yeah, so Bluetooth, the range is the big deal, right? Bluetooth is about 30 feet, 32, 33 feet. It's a big, huge difference there. Cost, it's probably comparable. You might be able to get some Bluetooth modules that are just a little bit less expensive. In part, your power consumption is going to be low, and then your device compatibility is the big thing, right? So your trade-off for extended range, now you can use it with your phone pretty easily. A lot of the modules will run off of USB, so you got Bluetooth built in. You don't have to, so it's going to lower your cost there too, right? Because you'll have your Bluetooth transmitter in your phone and the receiver on the robot. So that's pretty much, and then in terms of speed, they're probably comparable.
Are they comparable? Yeah, I've heard that Bluetooth can be a little laggy, but your experience is that it's
Yeah,
comparable.
I think maybe you get what you pay for.
Yeah,
to
in terms of Bluetooth,
a certain extent. Yeah.
And then the other wireless options, we've already mentioned these. We've got Wi-Fi, NFC, and GPS. Wi-Fi is the system that most people have in their homes, and of course, coffee shops and other places have Wi-Fi as well.
Yeah.
And then you can communicate. This is where the Internet of Things technology really starts to flower, I think, when you start thinking about a wired home and then having these devices that are all connected.
And of course, you can connect. You can be using Bluetooth in your device and then connect it through a PC to the internet or your local network. So you can get there with the other technologies as well. It's not like if you use RF, you can't connect to your network or control it, but you need one extra little step in there to do it. So.
And what's NFC? Maybe a lot of people aren't.
Yeah, near field communication, right? So you'll see that in a lot of the phones. Not sure about tablets as much, but definitely in the phones. And that's when I think of NFC, I think of people paying for things, going through the airports. It's kind of that thing where you see somebody tap the devices together to share a photograph or something like that. But it can be used to communicate lots of different types of information. It's not just photos or banking or whatever. But that's really close range, right? Yes. So Paul and I were talking a little bit about what would you use NFC for in a robot, and luckily Barry suggested, hey, if you want two robots to come together and communicate information, maybe they're setting up some strategy against this other robot, and they
or
need
romance,
to share.
they're
romantically
involved.
Romance.
That would be a good option.
So, but there would be lots of uses for NFC as well. But it's that close-up communication that you would establish that link.
Perfect. And then GPS. Everybody's familiar with GPS. That's the thing that a lot of us have in the car for navigation. You can use it in your robots in the same way.
Yeah, and it's not necessarily a communication, but we've talked about navigation as well in our last module, last session, for autonomously moving around in your area. So GPS is definitely a wireless. It's wireless.
That's right. That's for sure.
So so I think that round out those different technologies.
Yep. All right. So that's an overview. We wanted to just give you a kind of a thumbnail of what's available. If you were with us in the last module, we showed you some websites where you can purchase some of these things, and you can find a lot of these technologies and the components for them on those websites. So now what we want to do is focus on a specific RF technology called XB, and we're going to use XB as a means of demonstrating how this technology can work. And we'll walk you through a demo. Before we do that, we want to talk about some of the options and how you configure XB hardware and then part of the operational aspects of XB. So, Chris, you want to talk a little bit about what are the XB hardware options?
So, XB is a company, right, that makes these RF. They make other types of wireless transmitters and receivers as well, but their RF modules are referred to as XBs, and it's kind of an industry recognized technology, and we just picked it because it was well supported, and we're not saying, hey, this is the technology you should be using, but it was the one that we picked, and probably not unhappy about it. It works very well for us, and we are going to be showing you that. What we have is transmitter receiver pairs. You have a coordinator, which is like you'll have one coordinator in your network, and you can set up a full network of these things, and you have a router, and you can have a lot of routers, and then you have an endpoint. Endpoint is transmitting and receiving data, but it can't send that data to, it can't share it out like a router can, and it also can sleep. I'm not going to get into it too deep, right? Because we just have a very simple configuration that we're using. But there are different configurations for these. You can change the configuration of the modules by downloading different software onto them, so firmware. And then, so you can set up any of the modules as a coordinator, or a router, or an endpoint. The routers will transmit to each other. So if you had a router go out in your network, the other routers will fill in the gap. So it's pretty robust. And then we're going to go through. We're not going to go through the configuration process, but we're using a coordinator and a router in our pairs, both in our demo and in the MS Spider bot. And let's see, so the last thing on the slide is talking about the different modes of operation. You can be in AT mode, which is just an all kind of, I think always transmit, but it's probably stands for something else, or an API configuration, which is sending more packages of information. You can set up your security if you're worried about security. There's a lot of different things that you can do. So in general, big, nice, robust, well-established technology.
That's great. So does every XB environment have to have all three components, or can you just have a coordinator and an endpoint, or a coordinator and a router?
You only need two.
Okay.
Yep.
But
you do need a coordinator.
You do need a coordinator.
And you need something else.
Yeah.
And you can only have one coordinator.
Got it. But it can be a router or an endpoint.
Yep.
Either works. Okay, great.
Yep.
So let's move right into the demo. This is where we're going to get into kind of the fun stuff and show you how this wireless technology works. So,
all right.
Why don't you talk us through what we're going to do? We're going to be pairing a controller, a coordinator, and a router, correct?
Yeah. So the company, the XB Corporation, provides software to help you to configure these devices. We said that you can take a module and you can configure it in the different ways. So that same software can be used for communicating. So what we have is we have our coordinator plugged into our PC, and we have our router connected to our Arduino board, and we are going to communicate using the software from XB,
right?
To communicate from the coordinator, from the PC, to the router on the Arduino little demo.
Yeah, that's pretty cool.
So we're going to send it a command, and then based on what that command is, so let me make this software, let me make the code a little bit larger. So we have some lights, so now we can see that on screen. So we have two little LEDs. One is red, one is green. And what we're doing is we're saying if there's something in the queue, we're going to light up the red LED. If the message is the message we're looking for, we're going to light up the green LED. And then we also have a servo, in case the lights don't show real well, we have a servo that's going to run at two different speeds based on the information that it's getting. Now down in, and then we have message in and message out. I don't think we're using message out. We could be sending a confirmation message back to the coordinator if we wanted to. So we're just setting up which pins these are on here.
And again, we talked about this in previous modules, what all that means. So if you're unfamiliar with that terminology, just go back and watch the first few modules of this series.
Yeah, but really easy, right? There's different pin numbers on the Arduino boards, and we're just specifying which one, and then we're down here we're saying that we're using it as output, so we're going to be turning the lights on and off, and then we're just attaching the servo. So all straightforward stuff. We're using serial communication with the RF, right? So our it's a serial connection. Now we say, okay, if there's information available, so if there's something in the queue, if we've received some information, let's go ahead and say, okay, we're going to light our red light. Our red LED will light up if there's something there. Then we're going to wait a period of time, and then we're going to actually read that message, and then we're going to wait a period of time longer than that. Now we're going to check to see what that message we received was, right? Because we're going to say we're putting this message in. We're checking the value of message in, and we're going to compare that with the capital G. And these are actually I think it's an ASCII representation of a G. It's not an alpha numeric character, I believe. And then if it is what we're looking for, now we're going to turn the light green, and we're going to wait a little bit longer, and then a delay again. Oh, we're running the servo, I'm sorry. We're speeding up the servo motor.
Faster, yes.
Right? And then we wait. Now, if it's not the message we were looking for, right, so if it is the message we wanted, then if it's not the message we wanted, then we're turning the light off and we're stopping the motor.
Right.
And we don't turn the red light off, it looks like, there. But if the buffer is empty, then we do.
Got it. Cool. So we're only looking for one message, right, which is capital G. And
Yep.
otherwise,
Anything else will just say that there's something in the buffer,
but it won't turn
and
the light.
it'll light the red light. And then a little bit later, it compares what was in the buffer, because it reads it,
Right.
and compares what was with the representation of G. Yeah.
Yeah,
So the
then-
red light should light every time we
Right.
send it something.
Yeah, that's right.
The green light will light only if it gets what we wanted, what it was expecting.
Yeah.
Right. So we've shown the software, but we haven't shown pairing it up yet.
Yeah. So why don't we do that next?
Yep. So that's this other software. So we can see this. So now the first thing we're going to do, Paul, is we're going to look to see what's connected to our PC. So click this. So now it sees the our USB ports, right? And I'm going to deselect our Arduino board and select this other USB serial port. Say next. These are the configuration that it should be finding, right? And say finish. Okay, now you can hear things moving as it's searching for devices. So it's getting some signals as it's doing that. I'm going to say select and add device to devices. Now we can see that we found this coordinator 2. I'm going to select it. And it is reading the information off of that board, off that little module. And this is how it's been configured. So it's reading in the configuration data. So we could make changes to this configuration, but it's set up as a pair now. Right? And it has settled down, so it's cleared out the buffer. As it was loading up, it was receiving some information, so that buffer is now empty. I'm going to move over here to the command area.
This is all XP software, is that correct?
This is their software, that's right. Now it's saying open up a serial connection, so I'm going to actually connect it. So now we're connected to the coordinator. And now I can send it a little message. So now they're paired, ready to go. So if I send it something other than a G, we should see the red light, and the motor should go at a slower speed.
Correct.
Okay. And it should wait a little while, 5 seconds or whatever the delay was, and then it goes off. Okay, so that worked great. Now if I send it a capital G, which you can see there in the kind of this area, right? So I typed in whatever that was, a D. If I type in the capital G, we should first see that it saw something in the buffer. So it should go, the red light should light, and the motor should move the same way it did. But it should then look and see that it was in fact the capital letter G, or ASCII representation thereof, and it should then turn the green light on and go faster.
Right.
So here I go.
And the red light should stay on too, right?
Yeah, we didn't turn it off.
Yes.
All right, and the green light is lit. You can't see it very well. And now our green light is still going for a little bit here. At some point, it should go through and say, hey, there's nothing in the buffer, and everything should go off.
It should turn it off. That's cool.
But that's basically it, right? So again, with the letter G, and that's all there is to it, right? I mean, from a software standpoint, it was really very simple, right?
Yes.
The board that we're using, the Shield board, and maybe you can see this. I don't know. I might turn it the wrong way on you. So there's the little receiver. And this, so the receiver module, and you can kind of see they're labeled, right? R and C. Because they can be programmed to be either one, they're not indicated on the modules themselves, right? So we put a little label on there so that we knew which was paired. But you can see the Shield that was purchased for it has this little tiny switch on there because it's using serial in the same way that the Arduino board uses serial. Having a little switch that allows you to program the board without interfering with your serial RF communication is a nice little switch, right? Otherwise, you'd have to take the RF module off of the board while you're sending the program to
That's correct.
the Arduino board.
Now,
So,
it might not have been clear, but what we were doing was we were sending a signal to the little device that I had here in my hand. I'm showing. I don't know if you can see it. This little guy. And when Chris would press the D or the G, it would send that signal to this device, and then using the radio control would send it over to the other board that would make it do something. So we were actually using two radio devices, and they were talking to each other. Well, it's actually one-way communication, but the one was talking to the other to tell it what to do. So that's how it was. We did the demo. We made the operation work in that direction. Now what we're going to do is quickly talk about the SpiderBot, where we bring this together in an actual robot and show how you can use the radio wireless control to actually make the robot do certain things. Very similar to what we just showed you, but obviously it's going to be in a robot that's going to walk around and do some things. Before we go back to the arena, we want to talk about how we put the SpiderBot together, and then we'll show you it working all in kind of one place.
Yep.
So let's talk a little bit about how we developed the SpiderBot, some of the aspects of it. We're not going to go into a lot of depth of how this was put together, so we want to give you a quick overview before we show it to you.
That's right. So most everything that we've covered so far, so we've covered the different technologies that went into this. So you have everything that you need in order to build one of these.
That's
and we can throw up the different, when we share out the code, we'll share out the hardware that we used in these different things as well. But basically what it is each of the legs is using 3 servo motors. You kind of, maybe you can't see it. They each use 3 servo motors, so it can take little steps forward and backwards. Weight was an issue for us, so we made it out of a carbon fiber board, which gave us it doesn't seem like a flexibility of the board would be an issue, but the carbon fiber is nice and stiff, so it allowed for the legs to move and hold the weight of the little SpiderBot up without too much flexing.
Yeah.
Which turned out to be kind of important for us. So we have all with 8 legs, 3 motors on each leg, 24 motors. So we're using 2 different shields to control the motors. So we have our motor driver shield, and then we have the RF communication shield. And they're all using I2C. So they just need to be set up on different channels. Mm-hmm. And that's pretty much it.
Now, speaking of the weight problem, when you did an early prototype of this robot, you tried to make it out of plexiglass and it wouldn't stand up. I remember you telling me you were struggling. The
different servos as well. Yeah. Right? So we're using a micro servo with metal gears.
Got it.
All right, so it's a
little bit
relatively higher torque. There may be, I think, $6 to $8 a piece. So it's a more expensive robot to build than the others, just because of the different hardware that we're using on it. But it was fun, right? And we wanted to have something that was RF that was kind of more interesting, right?
Yeah.
But instead of doing the wheeled motion, doing the leg motion, it was a little bit more challenging.
Yeah, because you're working with a lot more servos.
See, I got you.
Yeah, you got to be talking servers now. A lot more servos. We're using the shields, and then we've added an RF board to it as well. So there's a lot going on with this.
And then there's the coordination of the leg motion, right? So there's some different things. So, but it does a few different things, which we'll see here in a second. And we're using RF off the PC the same way that we were doing the RF communication there. You can kind of see that there's a RF module here, and we have a paired same kind of deal. So you can see it's a little antenna poking up.
That's right.
Right? And you might have noticed that in our other one, in our little demo, the router didn't have a little antenna poking up. And that's one of the configurations that you can get with the XPs is the antenna is just part of the board.
Ah, perfect.
Right? So there are times when you might not want to have this big antenna poking up, right? It might be a space thing or it could be something else. I think maybe the range is affected just slightly by that, not too much.
Good.
Yep. So that's it. So we're going to make our trip over to the pit and watch the SpiderBot.
Go.
So hopefully that'll work.
All right. We'll see you over in the in Studio B.
All right. Here we are. We're back in the pit. And this time, we've come with the MS SpiderBot, which is our RF-controlled robot. See, what are we going to do? We got this all set up. I have my PC here. I'm going to be controlling it. Let's turn this bad boy on. All right, it's going to initialize. I'm going to move over here, and I will give it a command from my PC. Let's try forward, which is towards me. Let's go back. And I think we should spin. So what we're doing here is I'm sending a command from our XB module connected to the computer, which is the PC, which is the coordinator, and then I am receiving it on the module, the XB module set up as the router. So coordinator on the PC, router on this guy. Let's go forward. Let's speed it up just a little bit. Send it a 5. And let's try a left turn. That is not. That is a right turn. Back him up a little bit. Let's speed it up a little bit more. Spin again. And let's try a little bit more forward, and then crouch. And let's see if he can arch up. And back to a crouch. Back up. And he's going to do a kind of a left-hand turn. Back him up off the wall. This is just kind of an idle motion. So each of these different commands we're sending it, is programmed to do this. There's a lot of different options here, right, that we can do. These are just a few of them. And we can just stand still there. Again, we crouch down, start moving forward, turn left, back up. So you get the idea. That's pretty much it. And that's going to wrap up for this module, and we will see you back over in Studio A.
Well, welcome back to Programming Robotic Systems with Visual Studio. This is our final module. We're going to actually talk a little bit about what's coming. We want to talk to you a little bit about how we're thinking about robotics, sort of Microsoft's foray into the space, and where we see the industry going.
It's a whole embedded thing, right?
Yeah, embedded really is where the industry is going, but robotics is a good kind of hobbyist introduction to that space. So we want to talk to you a little bit about where we see things going in the future, and then we want some feedback from you so that we can develop the right Microsoft Virtual Academy courses to talk about the areas that are of interest to you. So we want your feedback as well.
Yep.
So let's just quickly talk about what we're going to go through here. We're going to talk a little bit about the Internet of Things. We're not going to say a whole lot about it. We've mentioned it in previous modules, but we do want to give you some ideas on where we see things headed and how robotics relates to that. We'll talk a little bit about the .NET microframework. Chris will talk about what is interesting in that space. Some tablet PC topics and some training there. We have a course that we've produced on integrating Connect with robotics and other systems. And then we want to talk about what other future MVA topics that we can cover in this forum so that we can reach the areas that are interesting to you. So let's talk a little bit about Internet of Things first and what that means. We've, as I said, we've mentioned this in previous modules. Microsoft's position on Internet of Things is to really talk about what's interesting to each individual.
Right.
So we call it Internet of Your Things.
Right. It doesn't have to be the whole internet.
That's right.
It doesn't have to be. You don't need to be looking at the connected devices, the weather buoys or the wave tidal buoys in Baltic Sea or whatever, right? It doesn't have to be that Internet of Things. It can be, your local. You were mentioning your thermostat, Paul.
Yes.
But it can be those things that you care about, that you want to see connected. Do you want to be able to turn off lights from your phone? Do you want to be able to do this or that? Do you want to control your robot, right, to do your little process or whatever? So Internet of your things.
That's right. And what we hope is that our audience, the audience that we're talking to today, you guys, the developers, will get into this space and start developing these devices and the software to go along with it. Because this is a huge opportunity. It's a huge area. And finally, the technology is there for hobbyists and individual developers as well as corporations to get into it and do a really bang-up job.
Entrepreneurs, right? Develop your own device that you can sell. And we've covered a lot of different sensor types, maybe not in depth, but we've introduced them at least, and we've given you some a base that you can grow your skills from. And so sensor networks is something that we might cover a little bit more as well. I mean, things like the XBRF modules are designed for sensor networks, and then can communicate to your PC, right? So you can be gathering your data either your shop floor or your home, whichever one. You can be developing the device that connects to a sensor network, whether it's this an improved thermostat or some other device that can monitor something or communicate information. It could be part of your aquarium or something like that, right? It's telling you whether your chiller in your aquarium is working correctly, what's the temperature, what's the lights, are they cycling correctly? Any kind of hobby, any kind of thing. Sensor networks, man.
And then what's an intelligent system service?
That is Microsoft's.
Yeah,
that's a cloud service which helps you to make sense of your data.
Right.
So that's kind of a nice little description, right? So you have sometimes you'll be in a business where you're tasked with capturing all this data, and then you set it all up, and you're capturing all this data, and then there's so much data it's hard to make sense of the data, and so this is a service that helps with that.
Great. So Internet of Things, you're going to hear that buzzword a lot in the next few years and months and years. And again, we think that the robotics hobby is a great introduction to that space, and we hope that you'll embrace it and start to do a lot of cool things with both the boards, the hardware, as well as the software. All right, let's talk about .NET micro framework and how that relates to the work that we've been doing in this module or in this course.
So .NET micro framework is so. If you're a developer and you're watching these video series, you probably understand what the .NET framework is, and the .NET micro framework is the subset of the .NET framework that works on embedded systems. So we mentioned in one of our early modules the NetDuino. We've been using the Arduinos, and there is a NetDuino which is pin compatible with the Arduinos, but runs the .NET micro framework. So if you're familiar with Visual Studio and you want to be programming in .NET C#, right? So now we're not programming in a version of C++. Now we're programming in C# like you're used to, using the .NET micro framework. It doesn't have to be a robot, right, for that kind of programming. It can be some of the other things that we talked about, Internet of Things. You can be programming the .NET micro framework will run on other devices as well. So there's lots of opportunities there. We might build your own controller, right? So maybe we're going to do an improved spider bot that has more natural movement. We'll use different hardware, make it maybe a little bit cooler, maybe do 3D printed legs and parts, and talk about how we designed that and how we built that, and now how we've improved the movement of the motion of the spider to make it look more natural. Things like that, right? And then another big buzzword, Paul, is wearables.
Wearables, yeah.
Right? So it's not just watches, it's all kinds of stuff. I think I read something that clothing items that are have some type of communication, whether it's Wi-Fi, I don't know what kind of communication, but there's lots of stuff out there. So a lot of that can be programmed with .NET micro framework.
And wearables are really popular now in the athletic industry as well as the health industry. So there's just a ton of opportunities here, and lots of cool things that you can do in the wearable space in both of those areas. Lots of cool things to think about. All right, and the next topic we wanted to cover very quickly is talking about tablet PCs and some training that we're offering in this space. I think most developers, at least developers that are associated with Microsoft technology, has heard about Kinect, and there's now Kinect for Windows. So you can use Kinect in a desktop environment. We had been talking about integrating Kinect into a robot, which there's a lot of opportunities to do some cool things there. What are some of the topics that we were addressing?
Yeah, we see there's a few here, right? Facial recognition, right? So that's something that the Kinect and the SDK help you to do, kind of out of the box kind of thing, right? I mean, there's some coding that's required there, but some out of the box functionality there. Voice control and responses. It's a lot of the things that you're with your Kinect that's for the Xbox. A lot of those things are enabled for Kinect to Windows. With the Kinect to Windows device, right? So in the SDK. So then you're programming it. You have access to those APIs, and you're programming that into your system, whether it's a robotic system that's going around, wandering around, recognizing people and talking to them, or it's just a application that you've written that does those things and runs on a PC or a tablet.
Yep. And the tablets are getting so small and portable, and they use a lot less power, but they're extremely powerful devices. So integrating a Kinect onto a small robot using the Kinect device and a slate. I have a little 8-inch Dell that's extremely powerful but very small. Is very easy now. It's a live option.
Yeah, and then Microsoft Research does a lot of the research projects they're doing. Are based on PCs, right? They're not embedded systems, right? So we kind of lump this in here with PCs, but they do some robotic stuff. They do, Paul and I talked to these guys about some of the things that they're working on, and so we're hoping that we could do maybe if we see some interest, do a series with MS Research where they come and they chat about different things that might be of interest.
Yep. So we're going to continue to talk to those folks and see what they're able to do, and if we can get them in the studio, we'll certainly let you know. So stay tuned to Microsoft Virtual Academy, and we can let you know what's coming on that space. And
then finally, we want to know if there's if you enjoyed the robotic stuff and you want more, we'd like to know that too.
Yeah, we're going to be posting the code that we showed you in this course, and we're hoping, again, we said this earlier, but we hope that you'll go out and try these topics and try to apply what we've been trying to show you here.
And improve them.
Right, and make them better. And we'd love to see what you're doing. If you want to send us some video of your robots, or you want to share your code, we would love to see all of that stuff. Yeah. So again, get out there, pick up some of the boards, pick up some of the software from the websites.
Use Visual Studio.
Yeah,
to program your robots, man.
Exactly, and we'd love to see. So send us your feedback, send us your ideas, send us your videos, and share your code, and we're going to get this industry off the ground, particularly when we start thinking about Internet of Things and all the,
it's a big deal.
Opportunities there.
Yep.
Thank you for watching.
Thank you.